Okay, so I'm back. Yeah, we just finished the tensor analysis stream a few hours ago, and here we're back with some more measures theory. Okay, so without further ado, let's get started. So where were we? Last time we finished defining Borel sigma algebra. Actually, last time we talked about sigma algebra, the definition of sigma algebra, and saw some examples of them. And in particular, there's a notion called the smallest sigma algebra containing a collection of subsets, also known as the smallest sigma algebra generated by a collection of subsets. All right, and then the most famous example for that, the most famous example of that are the Borel sets or the Borel sigma algebra. So the Borel sigma algebra is going to be the one that we encounter arguably the most down the road. I'm not going to repeat those definitions now because it's very likely that we'll encounter them later. Okay, so today we'll do some exercise too, I'm pretty sure. But here we're in this new section on measurable functions. So first, let's review a few identities for the inverse image. First of all, what is an inverse image? So the inverse image is a fundamental concept in set theory. So let's say f is a function from x to y. X is a domain and y is a codomain. And let A be a subset of the codomain. F inverse A is the set of little x in big X such that f of x is in big A. All right. So this notation by no means suggests that the inverse function exists. Okay, it's just a notation. F inverse of A together is a single object. Okay, we do not suggest that F inverse exists. The inverse image is well defined. It is a set. Okay, and here's a simple example which we went through last week. And here we have a result called algebra of inverse images. So these are the identities. As we can see, the inverse image is extremely well behaved. So the first one says the inverse image of a complement is the complement of the inverse image. Very nice. And the proof is rather easy. So in fact, these are standard exercises in a course, in perhaps the first course on proof writing. Every course on proofwriting should have that. And speaking of which, I don't know when, but there's an upcoming live stream on the basics of proofwriting as requested by some viewers. So, and in that, I will actually, would like to show the the existence of non-measurable set as the motivation for seriously studying proofwriting, because the first courses on proofwriting tends to be rather dry and boring, and it feels like you're just proving trivial things, and it can be perhaps not particularly motivating. I would like to give that example right from the start to see what kind of consequence can follow from these seemingly innocuous tools. Anyway, let's come back to the algebra inverse images. So basically, what I'm trying to say is the inverse images behave extremely well. Okay, so the inverse images behave as pretty much the way as you expected. The same cannot be said about images. Okay, if you replace big F, sorry, not F, just replace F inverse by F, it would not behave the way you want it. All right, so that's what we're trying to get to. So here we have the first property, as I mentioned. The inverse image of a complement is the complement of inverse image. And the second one says the inverse image of an arbitrary union. This is an arbitrary union, okay? The collection scripted A of subsets of X is arbitrary. It can be finite, it can be countably infinite, or it can be uncountable. So this works for arbitrary collection. The inverse image of an arbitrary union is the union of inverse images. So you can exchange the order of the union and F inverse. So that's pretty nice. And the same works for arbitrary intersection. So these are the properties. Okay. And last time we proved the first one. Okay. It's just a standard element chasing argument. Okay. I will not repeat it here because at this level, these proofs should be very straightforward. Okay. Okay. So let me just can I? Yeah. Can I maybe? This is too big, huh? This is too big. So 1 or 2, perhaps. Fit to height. Yeah. Okay, this is okay. This is an okay size, perhaps. Yeah. Yeah. It's hard to find a sweet spot. Okay. You know what? Let's just do it this way. In case somebody is watching it from mobile, can you give an example of showcase the image does not satisfy one of these? Sure. Why not? I think it's in one of my quizzes. So let's say, let's first define image. So f is a function from x to y. X and y arbitrary set. Define f, say, I'll use the letter b. Okay, f of b is the value f of x, the collection of value of f of x where x is in b. Okay, for any b which is a subset of x. So the claim is we have fa union of b equals fa is it, sorry, not equal, but a subset, but not equal. Union FB. Let me see if that's correct. So FA, F is a function that A and B are subsets of the interval. Give a counterexample. We meet again. Hi, Christian. Thank you very much. Hi again. Like, yeah, I still work 8 hours a day even when I'm on vacation, but I enjoy it. So I'm just trying to show that inverse images, sorry, not the images don't behave as nicely as the inverse images. So hang on, can I cook up a counterexample? I believe, yeah, it's in one of my quizzes in the community tab, but now I have to think about it. It's a subset and not equal. I guess it has to do with the function being one-to-one and onto one of the or fail to be one-to-one and onto, and this is when the strict inequality hold. Huh. Greetings from Mexico. Thank you. Thank you very much. You know what? Sorry, guys. I think I'm going to. I think I'll have to take a look at my notes. Where's my topology note? Please, guys. Or I can take a look at my own community tab actually. Sorry, guys. I can't think of a counterexample from my head right now. So go to the post. Yeah, so here's a quiz. Set theory quiz. The intersection property is false. The intersection property is actually false. If A intersect B equals F A equals intersect FB, that's false. So to see a counterexample, you can let A and B be disjoint. Okay, A and B be disjoint. So this way, the left-hand side is the empty set. The right-hand side is non-empty. Okay, so that's a counterexample. And actually, I think for union, you actually do have equality. I think for union, you actually do have, yeah, right here. Yeah, that's why I was struggling. For union, you do have equality. So this is actually a fluke. This is actually a fluke. So for images, this is an identity, actually. I was trying to think of a counterexample. I couldn't because this is actually equality. So, yeah, and for intersection, you in general only have a subset. Yeah, thanks for asking for a counterexample. This way, I get reminded of what actually is true. Okay, counterexample, just do that real quick. But for inverse images, you always have equality, so that's pretty nice. And Leo from Leo Lecture told me that there is a category theory explanation for that, which I'm very much expecting, very much looking forward to, because tomorrow he will teach me some category theory live. I'm very excited. So the counterexample is as follows. So f of x equals x squared. So okay, f is from R to R, all right? And let A be -1 to 0, and B to be 0 to 1. This way the intersection is just empty set, therefore F, the image of the empty set is still empty set. And of course FA intersect FB is non-empty. It's C open interval 0 to 1. It's not empty, okay? So that's the example. Thank you very much for raising the question. All right, so let's come to union sounds right. Yeah, union is right. So nothing is wrong with union, all right? So going back to Axler. So we have these properties, which will turn out to be useful when we study measurable functions. Next up, inverse image of a composition. Because this is interesting. I'm not super familiar with this one, so let's try to prove that. F is from X to Y, and G is from Y to W. Okay, and then it says the inverse image of the composition of G and F of A is this thing. I mean, it feels intuitive, right? You can draw a diagram to illustrate the situation. So this is Axler 2.34. F is from X to Y. G is from Y to W. And then we have this formula. The composite function, G composite F, taking inverse image of A. That's the F inverse of G inverse of A. All right. So let's draw a diagram to illustrate the situation. So you have the set Y, set X, okay, set X, set Y, and set W. All right. So you have two functions. This is F, this is G. Okay, so first of all, inverse function of inverse function of what is G? Look, what is G composite with F? Well, G composite F is, of course, by definition, G of f of x. So G of f is a map from x to w. And therefore, the image, I'm not saying the inverse function exists, but once again, if you're talking about the inverse image of this of the set A, it must mean that A is a subset of W. Okay, sorry, yeah, it says A is a set of W. So let's put that here. So let's say this is A. A is a subset of W. What is the inverse image of the composite function? Well, you first pull A back into Y. So this will give you a G inverse of A. And then you pull everything here back into X. And that gives you F inverse of G inverse of A. So it feels intuitive. It should behave this way. Right. But let's now just prove this identity. It's a double containment argument, or we can use a bunch of if and only if. Okay, so let's use a double containment argument just to be safe. Okay. So let's say I want to prove one direction. You simply let x to be in the left-hand side, the set on the left-hand side. Okay, this simply means the function G composite f acting on x is in A, which is the same as saying G of f of x is in A. Okay, we want to show this is in the right-hand side. We need to show x is in here. So what does that mean? So it means that f of x is in the G inverse of A. Okay, and hence x is in f inverse of G inverse of A. So there's that. So that's what we wanted. That's one direction done. Pretty easy. And let's do the other direction. So let x in the other direction, f inverse G inverse of A. So f of x would be in G inverse of A. And x is in, sorry, not x, but G of f of x would be in A. And this is the same as saying the composite G composite f of x is in A. So we're done. Okay, so it's super straightforward. Okay, should be just an introduction to proof level of material. So we're okay with this. Okay, so finally it's time to define the main star of the show, measurable functions. So last time we mentioned that in measure theory, we have the notion of sigma algebra. And pretty much these notions, right, they have the probabilistic counterparts. I mean, they're literally the same mathematical object, just called different names. In measure theory, we say sigma algebra. Of course, in probability, we also say sigma algebra. But the members of sigma algebra are called events in probability theory. And now we talk about measurable functions. Okay, measurable functions in probability theory are called random variables. So this is something that is also going to be hugely important. Okay, measurable functions. The next definition tells us which real value functions behave reasonably with respect to sigma algebra on their domain. Definition: measurable function. Suppose Xs is a measurable space. Recall what this means. X is an arbitrary set. S is a sigma algebra on X. All right, and f is a function from X to R. A real valued function on X is called S measurable, sometimes just measurable if S is clear from the context. If what? It says if f inverse of B is in S for every Barreal set B in R. So what it's saying is You essentially have two measurable space in this definition. First is XS. The other measurable space is R equipped with the Barreau sigma algebra. So you can write R, so you can write the ordered pair, okay, R B. I think that's the notation, right? The scripted B for Barreau sigma algebra, or BR. Sometimes we write BR. Is there a notation for that? Okay, it does not introduce a notation, but I think it's pretty common in analysis to write the Barreau sigma algebra as BR, B of R. So that's the most common setup when you do measure theory on R. So R equipped with the Barreau sigma algebra. So the thing is, you have two measurable space. This is a measurable space, and this is another measurable space. The function is measurable, right, if the inverse image of all the Barreau set are also measurable. The inverse image of Barreau sets are all members of the sigma algebra S. Love you, bro. Thank you very much. Or simply boldface B. Yeah, simply boldface B. And it's also a notation for sigma algebra. Although in my experience, it is very common to use scripted letters like this one for collection of sets. Okay, it's like here Axler use bold R for the set of real numbers. You also very likely have seen double strike notation for R. I use this pretty much all the time to denote real numbers, and double strike for C. And yesterday we even did the quaternion, right? Double strike H to denote a set of numbers. And here we have, if we have like a set of sets, a collection of sets, right? Set of sets sounds a little bit awkward. So a collection of sets, including topology. Topology is also a collection of sets, in particular collection of open sets. We use scripted letters. All right, so this is what it says. Remember, what are Barreau sigma algebra, by the way? It's perhaps a good time to review what a Barreau sigma algebra is. The Barreau sigma algebra is the smallest sigma algebra that contains all the open subsets of R. Okay, so you can think of open subsets as nice sets in R. And because we want to do measure theory, we want our sigma algebra to contain them. Open sets themselves, the collection of open sets themselves, do not form a sigma algebra. Why? Well, let's review the definition of sigma algebra. The sigma algebra definition says it needs to contain the whole set X. It needs to be closed under, sorry, that's a theorem. Where's the definition? The definition says it needs to be closed under complement, and that fails immediately for open sets. The complement of open sets are not open. So the collection of open sets themselves, unfortunately, do not form a sigma algebra. So we want our sigma algebra to contain open subsets. So we define ourselves the Barreau sigma algebra. This is the smallest sigma algebra that contains all the open subsets. All right. So these sets. So the idea is we can remember in the sigma algebra, sets are closed under. Sigma algebra is closed under countable union. Countable union is very useful for approximating sets. Right, think about that. So think about here, you have this nice little example. So let's say you wanted to, actually we have a question. We have a question in the problem set. It is perhaps more instructive to look at that example. In particular, in that example or slash question which we solved last time, you can approximate a set that is not easily visualizable using countable unions of open sets. Right here. So here f is an arbitrary function, and in question 12, which we did last time, so go check that out, we're interested in a set of points at which f is continuous. And because f in general can be very complicated, this set of continuity might not be so easy to visualize. Right? But that's okay. We managed to show that the set of points at which f is continuous is a countable intersection. Okay, it's a countable intersection. The countable intersection, countable unions are very useful constructions for approximating a complicated set using more well-known sets. So every GK here is open. That's part A, and it turns out that this set, which is a set of points at which f is continuous, is a countable intersection of open sets. We like that sort of thing, right? So let's come back to the definition of the measurable function. We established that the Borel sigma algebra contains nice sets. These are the sets that are either open or actually it can be closed too, right? Because it can be closed. But anyway, the point is the members of Borel sigma algebra are nice fellows. Now, these are nice fellows in R. Actually, you know here, coming back here, that's the definition of measurable functions. So the Borel sets, these are nice fellows. The inverse image of B are required to be in the original sigma algebra. This way we call f is measurable. This way f is measurable. So let's think about the motivation here. Okay, I'm going to use a probabilistic example. So imagine you have a sample space omega. This is a rather complicated set. Okay, omega is the sample space. Every element in omega are called outcomes. Little omega, these are called outcomes. And now let's consider a real line. Consider a real line. A function big X, actually a function big X, I'm using the probabilistic notation. Big X stands for random variable. Okay, X maps from the sample space to R. Okay, so in probability theory, we wish to calculate something called the CDF. Okay, we wish to calculate the probability of big X less than or equal to little x for every little x. Here. So we wish to assign a probability to it. Right? So this set, namely big X of omega, belongs to the interval minus infinity to little x, needs to have a notion of size. Remember last time we said this sigma algebra is going to be the domain for measure. We're only going to assign measure to members of sigma algebra, not the whole power set, because that's too much. That causes trouble. But this is nothing but the inverse image. Okay, so the set of little omega such that x omega is in minus infinity to x is nothing but the inverse image. This is just the inverse image of the interval minus infinity to x. So the idea is the inverse image needs to have a well-defined size. The probability measure is defined on the sample space. And now we are measuring the size of the inverse image. So that's why we need this definition. We need the inverse images of nice sets on R to also be nice in the original measure space. Okay, hopefully that provided enough information, enough motivation for the definition of measurable function. But real sets are nice, and we want the inverse image or pre-image of Borel sets to also be quote-unquote nice. Okay, we wanted to avoid the crazy non-measurable sets that we've seen in the previous section. Okay, so that's the idea. Okay, so let's write down the definition in our notes and do some examples. Okay. Hi everyone, I'm not staying long. It's late where I live. Hi, Wendelin. Thank you very much for stopping by. Okay. Anyway, here we have the definition of measurable function. And this is important because eventually we'll use a Lebesgue interval. Exactly. This is super duper important. Anyway, these are absolutely fundamental for measures theory. I'm very pleased to see there were streams on quaternions. Well, yesterday I was, I was very rusty when it comes to quaternions, and to be honest, my understanding was not very strong to begin with. A lot of people helped me out in that stream. Okay, we didn't do super deep quaternion introduction. Okay, we just define the quaternions and see how it encodes the 3D rotation. Okay, if you wish to see some like baby Lee theory there, you'll probably be disappointed. So yesterday was just a purely computational introduction to quaternions. It's like introducing complex number for the first time. All right, so you know what? Let's try to do some example for the measurable functions. Definition. X scripted S is measurable, is a measurable space. Okay, be precise with the terminology. This is called a measurable space. Later on, we will see something called a measure space, the different things. F from big X to R is so-called S measurable. If the sigma algebra is clear from the context, then S can be omitted. If for all B that's in the Barreal sigma algebra of R, F inverse of S is in, sorry, not F inverse of S, that's nonsense. F inverse of B is in the sigma algebra scripted S. All right, these are the examples. Let's verify them. So suppose you only have two elements in S. So this is what we call the trivial sigma algebra. Examples. This is definition 2.3.5, 2.35. Examples 2.36. Okay, 1. If S is the empty set and X, then the only S measurable function are constant functions. Then the only S measurable functions are constant functions. Okay, so this is interesting. Why is that? First of all, let's try to show this. Okay, so first let's show constant functions are S measurable. And imagine what happened if you have a non-constant function. There's the only S measurable functions from X to R are constant function. Why? Okay, so this is an only if and only if statement, basically. So let's prove that. Let's prove one direction. So so 1. Okay, assume F from X to R is constant. Let's look at the possible inverse images. Assume this is a constant. Say f of x equals a for some a in real. What's the preimage? Let's take an arbitrary preimage. Okay, let's take an arbitrary Barreal set. Let B be a Barreau subset of R. Okay, this is not good. Scripted letter. Let B be a Barreau subset of R. Want to show that. Okay, want to show that F inverse B is in S. Need to show. Is either empty or X. That is to say, is either empty of X. Well, let's think about that. So if, let's say, A is in case, because f of x can only take one value, so if A is in B, and that's the only value f can take, then so f inverse of B is what? It's just f inverse of the singleton A. And because every x takes the value f, for every x, okay, for every x here, for every x in big X, f of x equals A, the inverse image is just big X. Right? Actually, let's draw a picture. So this is what we typically have in mind when we think about a constant function. So here big X is visualized as the x-axis. It doesn't have to be a subset of R, because it can be an arbitrary set. The idea is f of x is flat, is just equals A. This is f of x, the graph of f of x. Okay, and now we are picking a Barreau subset. The Barreau subset, you can think of it as a subset of the vertical line, the vertical axis. This is B. It doesn't have to be an interval. The idea is if A falls in B, then the inverse image of B is the whole X. So that's the first case. And then you got the second case. Obviously, A is not in B. Then F inverse of B will be what? Because A is not in B, then that means no value of F falls in B. It's just F inverse of the empty set, which is empty. So these are the two possible cases. And both of them are elements in scripted S. So therefore, this is shown. So indeed, therefore, constant functions are measurable. So constant functions are scripted as measurables. All right. Second, assume f is measurable. How can f behave? Right. So that's the second question. You assume f from x to r is measurable. Is S measurable? For S equals the trivial sigma algebra. Right, we need to show that f is constant. Okay. So I guess the best way to do that is to use, and perhaps the best way to show that is to use a contradiction argument. Like, suppose for a contradiction there are two x values with different f of x values. Suppose for a contradiction. That there exists x1 not equal x2. Okay, so it's just say x1, x2 in big X, with x1 not equal x2, and f of x1 not equal fx2. That's the same as saying f of x is not a constant. All right. So so we need to construct two Borel sigma. To find two Borel sets, or let's find a Borel set whose preimage is not in S. It's neither empty or X. Okay. So let's do that. The easiest example would be, let's draw a picture, is to use an open interval that contains one of the f of x or f of x1 or f of x2. So that's the idea. So imagine, I suppose the function has two values. You can always separate 2 points with open set. Exactly. Yeah. That's the Hausdorff property, isn't it? So here, let's suppose x1 is here. This is f of x1. And this is x2 is here. This is f of x2. Right. So we can just pick an interval. Pick an open interval that contains f of x1 but not f of x2. You can always do that. Let B be an open interval that contains f of x1 but not f of x2. What's the inverse image of B? Well, we just need to show the inverse image of B. Suffice it to show that the inverse image of B is not empty nor X. So first, the inverse image of B is not empty. Since f of x1 belongs to B, i.e. x1 belongs to f inverse of B. There's that. Second, you have the f inverse of B is not the whole set either, because x2 is not in there, since f of x2 is not in B, i.e. x2 is not in f inverse B, so it can't be the whole set either. So therefore, f is non-measurable. Is non-S measurable. Is not S measurable. Wait, singletons are Borel too. So we can actually get rid of the. Yeah, that's you're completely right actually. Yeah, this is overcomplicating things actually. You know what? We'll take that. Singletons are Borel set too. Yeah, I will keep thinking about open sets, but it's actually unnecessary. Okay, so yeah, just pick B to be the singleton. pick B to be f inverse of x. F inverse of x1. Sorry, just f of x1. F of x1. The singleton. Yeah, singleton works. Yeah, you're totally right. Then then you have x1 is in f inverse b, but x2 is not in f inverse b. So, which means f inverse b is neither empty or x. Yeah, so this is easier. Very nice. Singletons are Barreal of a real set. So this way, f inverse of b is not empty or the whole set, i.e. f inverse of b does not belong to the scripted S, therefore f is not S measurable. So basically this example says if S is the trivial sigma algebra, f is measurable if and only if f is constant. Okay, this is a simple example. This next example, if S is a set of all subset of x, then every function is S measurable. But this is trivial, because if S is the power set of big X, then of course every inverse image falls in the power set, so that's trivial. So these are the extreme situations. Of course, in reality, you choose your sigma algebra in a way that it includes more functions than just constant functions, but not every function either. So there's that. Okay, so let's actually look at the third example. Let me finish writing the second example. The second example is very easy. If S is the power set of X, the same as every function f from big X to R. Hi George. Hi George Pang. You are the first one, I think, who asked for measure theory material on the channel. Okay, so the third one, as we mentioned, that's the middle ground here. If S, okay, that's a collection of four sets, is empty, minus infinity to 0, open interval, and 0 to infinity, close interval, which is a sigma algebra on R. Oh, by the way, this is a sigma algebra on R. Let's check that too, okay? We'll check that. Then a function f from R to R is edge measurable if and only if f is constant on the two half intervals. Okay, so that's an interesting example. That's interesting. Let's write that down. If S contains four elements. I believe last time we proved a proposition, a simple proposition, which is helpful for this situation. That is to say, if a collection of sets is finite, here, this is a finite set, it only has four elements. Any constructible set, what's a constructible set? I have no idea. Every constructible set is Barreal. Hi, Zigzag. I can't see your face. No, it's simply not shown. Sorry, I don't do webcams, not anymore. Because there's already tons of stuff on the screen. Like adding my face would just be distraction. Focus on the math. So yeah, if S is that, then F from R to R is as measurable if and only if F is constant. Any set that doesn't use axiom of choice in its description. Oh wow, is that strong? I know, like the I mean, I never seen this result. It's actually pretty. I don't understand either. What is the difference between the squiggly line and the other squiggly line? This thing, this is big S. This is scripted S. And the bracket, this is a collection of set. Now let me just write down this sentence. If and only if F is constant on minus infinity to 0, and F is another constant, perhaps constant on 0 to infinity. So this, you mean this squiggly line? This is just scripted S. The bracket, we have tons of bracket here, but basically we're dealing with this collection of subsets of R. Right? Every element is a subset of R. Here we have 4 such subset. This bracket, this is just an open interval sign, huh? No, no. So this is open interval. So that means greater than. So okay, this just means this is rather basic. So this is x, just x less than x in real. Okay, such that x is greater than minus infinity, less than 0. So it just means the negative reals, this part of the real line. If it's a square bracket, then includes 0. So square bracket would include 0 and all the way to the right. Okay, and when you list the elements in the set, you use curly bracket. So when you use curly bracket here, right here, if you use curly bracket, it means the stuff in scripted S are these 4 sets: the empty set, these 2 intervals, and R. Okay, so that's basic set theory notation. You know what? I don't know when, because right now I have to figure out my schedule. There's going to be a basic a stream on basic proof writing shortly. Okay, I'll explain the notations of set theory and whatnot. Okay, yeah. So if you're struggling with this, I hate to break it to you, you're perhaps not ready for measure theory, but I'm glad that you stick along. Okay, and there's no such thing as stupid question on this channel, even though this is basic, but you know, nobody knows this from their mother's womb, as we say in Chinese. Okay, so you all learn this stuff at some point in your life. You all have to learn this stuff at some point in your life, and that point can be different for anybody, which is totally fine, right? And I'm glad that you raised the question. Thank you very much. Just checking from time, you're hardcore. Maybe. Okay, so we're trying to prove this is S measurable. Because F is S measurable if and only if F is constant on these 2 intervals. Yes, Christian answered that question perfectly. So let's try to, first of all, verify this S is indeed a sigma algebra. Verify S is a sigma algebra. Last time we showed something. To show a finite collection is closed under countable union, you just need to check whether it is closed under pairwise union. That's enough. Okay, so first of all, R the whole set is in scripted S. So we're good. And second, check closeness under complement. Close under complement. Yes. All right. So let's write that down. Just list all the possibilities, right? So because there's only 4 elements. So here you can write this is write a set. Let's call it maybe let's call it A. Okay, A is a subset. Sorry, not a subset, but an element in scripted S. And here you have the complement. Complement sometimes is written as AC, but here in Axler we write R minus, just use set difference, R minus A. The empty set taking complement is just R, which is in S. Minus infinity to 0 taking complement is 0 to positive infinity. 0 to infinity taking complement is minus infinity to 0. And lastly, you have R taking complement, you just get R. Sorry, just get empty set. In fact, it's made of 2 sigma algebra, which is kind of the hint why the conclusion. What do you mean by made up by 2? You mean the union of 2 sigma algebra? I'm not sure. Okay, anyway, that doesn't matter. 3. Let's check closeness under union. So for that, you do a table thing. You just need to check pairwise union. Okay, and because union is symmetric, so you just need the upper triangle, if that makes sense. Yeah, that's okay. That's totally okay. So you have empty set minus infinity to 0, 0 to infinity, and R. Okay, empty minus infinity 0, 0 to infinity, and R. So let's just do the union in the upper triangular region. That's enough. So here, empty union anything is the same thing, like so. Okay, here you got this is minus infinity to 0, union 0 to infinity is R. This is also R. You can find that you get R. So everything here is in the S. Okay, so we're good. This is indeed a sigma algebra, so that's checked. And now you need to show f from R to R is S measurable if and only if f is piecewise constant. Okay, so let's do what we did in the first part. All right. So so 1. Okay, assume f from R to R is defined as follows: is f of x equals, say, a. If x is in minus infinity to 0, that means x is less than 0. Okay, say b, if f is greater or equal to 0 for some constant a, b in real. So suppose you have that, and we want to show f is S measurable. Need to show. Why don't you check the diagonal line? Well, if you take the diagonal line, the union is just itself, and all these sets are in the sigma algebra. Union with itself is itself. And if you take the opposite order, the union doesn't change, right? Union is commutative. So you just need to check all 6. That will be enough. Okay. Here you need to show f is as measurable. So how do we do that? Well, you need to let B to be a let. Okay, let B be a real sigma algebra, be arbitrary. So this is what we have here. So we wanted to show, need to show F inverse of B is always in S. There are probably going to be some cases going on. Okay, so here, because f of x has 4 values, like see how we did the constant case, the first one, right? So we consider, okay, A is in B, A is not in B. Let's consider the situation of how exclusive situation, okay, the mutually exclusive situation of how A and B can fall into B. So there are 4 cases. Case 1, A and B are both in B. A and B, these 2 real numbers are both in the set B. That's the first case. Let's first write down all the cases. So A is in B, B is not in B. Third case, A is not in B, B is in B. And lastly, neither of them are in B. Okay, so for each case, the situation for the inverse image is quite clear. Okay, so the inverse image of FB, inverse image of B in this case is, well, if it contains A, then it must contain all the negative axes. If it contains B, it must contain the non-negative axes. So that's just real, which is in S. And the rest can be done analogously. Okay, so there are 4 cases. Okay, so the second case, F inverse of B, is just the minus the negative axis. It cannot contain the non-negative because otherwise it would include B. So that's in S2. Third case, F inverse of B would just be the non-negative axis, which is in S. And lastly, nothing can be in B. It's just the empty set, which is also in S. So that's done. 4 cases are done, so that's easy. All right. Okay, so to prove the converse, what do we need? To prove the converse, so to prove the converse, we want to show that if f is S measurable, then f has to be constant on both pieces. Okay. 3. Do we suppose A? It doesn't have to be. Doesn't have to be. If, let's say, suffices to prove A and B are not the same, right? If A and B are the same, then f is constant, which reduces to example 1. Right? If f is constant, then the inverse image can either be the whole set or the empty set, which is still in scripted S. Okay, so you know what? Let me just say, suffices to prove the case where A and B are not the same. Here I implicitly use the assumption that A and B are not the same. Thank you. Can we measure love? No, you cannot measure love. Love is non-measurable. It's not additive. Okay, exactly the same reason why outer measure failed to be a measure. Anyway, so this is mathematically proven, by the way. Okay. So the second aspect of the proposition is to show that. Oh, hi Leo. I'm glad that you are in the stream. I'm very much looking forward to tomorrow's lesson. So love is non-constructible. Yeah, because love requires choice. Love needs choice, exactly. Cannot be forced. Um, okay, so assume f from R to R is S measurable. All right. I need to show f is constant on each interval. On each of minus infinity to 0 and 0 to infinity. All right. All right. So how do we approach this problem? I would like to use a contradiction argument as well. So let's say if you have f being non-constant on any of the two intervals, then what happens? Right. So that's first of all, how do you formulate a contradiction? We can say, suppose for a contradiction that f is non-constant on, say, minus infinity to 0, and the other case would work analogously. Okay, so suppose for a contradiction that f is non-constant or not constant on minus infinity to 0. Then what happened? Well, say for say f of x1 not equal f of x2 for some x1 not equal x2 and x1, x2 less than 0. Right? This means f is not constant on the negative axis. Then you can apply Wendelin argument for example 1. Right? So this consider the Barreal set f of x1. This is the Barreal set. What's the f inverse of b? Well, f of inverse of b will certainly contain x1, but not x2. But not x2, which means the f inverse of b is not the whole minus infinity. If you have time, please make a video on your views about the work of Yu Deng. Fields winner, thanks. Okay, I'm not sure if I'm intelligent enough to to make comment, but I guess if I'm going to make a video about that, we can. I mean, you know what? Perhaps it's better for a live stream. You know what? Because it's yeah, George, if you want to talk about it, like message me on Discord if you want to see a discussion. Because I mean, let's be honest, my level is not as high as a Fields medalist. Okay, I'm very much likely to make ignorant comments about their work. This is totally possible. So I would like to have like open discussion of what is that about. Okay, anyway. Are you going to discuss category in general with a particular aspect in mind? Categories here. I don't know. I don't know. When it comes to category theory, I'm pretty much blank paper. Okay. I'll follow Leo's lead. I was just asking, at this point, I can only ask very generic question, like what would be the prerequisite? Okay. What is it good for? That sort of thing. And yesterday, I just learned that categories aren't set. Okay. I thought category is a very, very large set that includes so many different constructions. That was my understanding, but apparently that's false. So my sort of a default language when it comes to thinking mathematics is very much set theory and naive set theory. Okay, because I don't have a very strong background in logic, mathematical logic. Yeah, so yeah, I was talking about a bunch of things. That would be great. Awesome. Thank you very much for preparing the stream. Sometimes category they can be. Yeah, this still you see, it's very murky for me when it comes to categories there, and also what is it good for? And it doesn't have to be say what is its practical application. This is not what I'm asking for. Okay, so what I'm saying is what are perhaps some of the consequences that can help us understand fields that aren't implicitly category theoretic. Okay, thank you very much. Yeah. So, so if you guys interested in the field stuff, we can have like an open seminar to discuss. Everybody can contribute. Okay. Anyway, so actually here. So x1 is in the inverse image of V, whereas x2 is not in the inverse image of V. Okay. So this means F inverse of B is none of the elements in S. Okay, so let me just write it this way. Since F inverse of B contains x1, F inverse of B contains x1. That's a negative number, so it can't be the empty set. It cannot be the empty set. It cannot be the non-negative axis. And since F inverse of B does not contain x2, it cannot be the negative axis or the whole real. So therefore, F inverse B is not in S. There are only 4 possibilities. It does not fall into any of them. Therefore, F is not S measurable. So we're done. Okay, so that's the full proof. Okay, once again, these are very easy to verify. All right, so let's continue. I plan to be passive aggressive. Okay. All right, that's funny. Okay, here, another class of examples come from characteristic functions, which are defined below. The Greek letter chi is traditionally used to denote a characteristic function. Sure. Characteristic function chi-e. This is like the indicator function in stats. Suppose E is a subset of X. The characteristic function of E is the function chi-e from big X to R defined as follows. So it's like turning on a switch, right? So E is an arbitrary set. Okay, so here there's no sigma algebra, no nothing. Okay, it's just a big set X and a subset E. If X falls into big E, if X falls into E, then the characteristic function returns 1, otherwise 0. A set that contains x, the set x that contains it is not explicitly included in the notation because big X is always clear from the context. Okay, so this is a notation for the characteristic function. Let's put that down. Characteristic function. In probability theory, once again, we of course called it the indicator, which is super useful. Okay, there's a function from big X to R, chi e of little x equals 1 if x is in big E, 0 if x is not in E. Okay, so there you go. E is a subset of X. Often characteristic is short for indicator for the Fourier transform of the indicator function, or for the Fourier transform of the indicator function. Yeah, characteristic function in probability theory has its other definition. It's a totally different thing. A characteristic function in probability theory goes something like this: is the expected value of e to the I5, e to the I tx. We call it phi of t. It's the Fourier transform. That's the expected value. Anyway, that's too deep. Okay, that's too deep. There's nothing of that sort yet. But would x not be in E? It has something against E. Well, x in general is just an arbitrary point in big X. It can be in E or may not be in E. Right? To think of E as an event. Think of E as an event, and big X is the sample space. The sample space is the collection of all possible outcomes, and E is a sub-collection of outcomes. Right? So if little x is in E, we say the event E occurs, and the indicator for that event turns 1, otherwise it's 0. Yeah, in probability, it's a Fourier transform of probability density. Right, so this is a confusing name here. In probability theory, characteristic function is the Fourier transform. But here, that's too deep, okay? It's just a simple indicator. Unfortunate naming, considering how closely related the two fields are, okay? Anyway, so here you have another example, inverse image with respect to a characteristic function. So here we have, once again, this is very similar to the last example we did, right? The last example is, well, it's not the characteristic function, but it's binary valued. It equals constant on one piece and another constant on another piece, right? So it's the same idea. So we'll not write down this example. If B is a Borel set, actually, it doesn't even need to be a Borel set. It just has to be an arbitrary subset. Okay, bye Leo. Thank you very much for joining the stream. Hardest part of anything is naming, yeah. Good names are hard to come by, indeed. And bad names confuses the heck out of people. So here, these are all the possibilities if, say, both 0 and 1 are in B, then the inverse image is big X itself, the full set. If 0 is in B and 1 is not in B, then that's the complement of E. If 0 is not in B and 1 is in B, then it's E. If neither of them are in B, then the inverse image is just empty. Okay, so you can see that this is in fact, perhaps this is a quicker proof. Okay, we should probably use this method to do the previous examples, but that's okay. Right. So here we listed the inverse image as a function. So you see, this is a function. This is the function that takes sets as an input and returns another set. It's actually a very economic way to write it. You don't need to write all these cases, right? I mean, these are still cases, the same thing, but just more efficient notation. All right, so you can see chi e is S measurable if and only if E is in S. If E is in S, then everything works out. If E is in S, then X minus E is automatically in the sigma algebra because sigma algebra is closed under complement. So, okay, so we're not going to dwell on this anymore. Here, the definition of an S measurable function requires the inverse image of every Barreau subset of R to be in S. Exactly. The next result shows that to verify that a function is S measurable, we can check the inverse image of a much smaller collection of subset of R. So that's pretty nice. That's pretty nice. Remember, by the definition alone, in order to check a function is S measurable, you have to show that for every Barreau set B, F inverse B is in S. And in general, Barreau sets can be pretty complicated. So using the definition alone can sometimes be a chore. So we wish to reduce our workload by considering the next proposition. Here's what it says. Here it means we check the inverse image of a much smaller collection of subsets. That's already enough. You don't need to literally consider a general Barreau subset. All right, here we go. Suppose big X and S is a measurable space, and f from X to R is a function such that the inverse image of a to infinity. Right, so this is a semi-interval, semi-infinite interval is in S for every a. Then f is S measurable. Right, so this is a much smaller class. Right, the collection of all semi-interval of the infinite interval of the form a to infinity. This is a much smaller class of sets compared to Barreau sigma algebra of R. So you just need to check, okay, all of these sets have their inverse image in S, then you're done. So that's pretty nice. Let's take a look at the proof. All right, so let scripted T be the collection of subsets A in R such that F inverse A is in S. Okay, so interesting. So this is the collection of subsets whose inverse image is in S. So you can think of this way. So this is your setup. You have X, okay, and this is R. What we want is the kind of subsets on the real line. Hi, Hiroshi. Thank you very much for joining the stream. Good to see you again. So A is a subset in R. We want the inverse image to be in the set S. Okay, the collection of such subset A is called scripted T. We want to show that every Barreau subset of R is in T, and that will be done, right? Because the definition of S measurable function requires that every Barreau subset has this property. So now we're just considering the kind of subset of R that has this property in general. So if a Barreau set falls in scripted T, then we're done. Okay. To do this, we first show that scripted T is a sigma algebra. Now, this is a sigma algebra, actually. To verify sigma algebra, you just need to check the three axioms. And here you can see it requires some properties of the inverse image, which is quite nice. Did you see that Canadian won the Fields Medal? Did you know him? No, I don't. No, I don't. I didn't have time to follow that, actually. But well, I'll take a look at it. Yeah, already somebody mentioned that, and let me know if you guys want to have some sort of seminar discussion over that to take a look at the work of that guy did. Yeah, I actually I don't know him. He's probably, I think he's a prof at U of T. That's as far as I know. Somebody mentioned that to me. Old classmate mentioned that to me. But I just didn't have time to take a look at his stuff yet. All right. So verifying T is a sigma algebra is a straightforward task. You just need to check the 3 axiom for sigma algebra. And that's this part. So we will do that ourselves. So it looks like we should be able to do that ourselves. All right. It says by hypotheses. By hypotheses. Okay, well, what's the hypothesis? Oh, here. By the hypothesis says F satisfies this property. F inverse from, I said everyone knew each other in Canada. Oh no, it's a big country, man. Over 30 million people. F inverse from A to infinity is in S. So this just means for every A to infinity is in scripted T. This is in scripted T. So there you go. Therefore, T contains this particular collection. And because T is closed under complementation, indeed, that's because T is a sigma algebra. So it also contains intervals of the form minus infinity to B, where B is a closed endpoint. This totally makes sense. Because the sigma algebra T is closed under finite intersection, yeah, we proved that earlier. So closeness under countable union is in the axiom, which implies closeness under finite union, which together, combined with De Morgan's law, shows that sigma algebra is closed under finite intersection. Yeah, that's true. So it's closed under finite intersection. So taking the intersection of A to infinity and minus infinity to B, we see that T contains the half open, half closed interval A to B. So this sort of interval is also in T. Okay, and I'm kind of lost of where we're going, because we wanted to show that F is S measurable. So by definition, we need to show every Barreal sigma algebra, every Barreal subset of R is in T. Okay, and here we have what? Here we have what? So we have T contains intervals of the form A open endpoint to B closed endpoint. Okay, and you can write intervals such as intervals A to B, open interval, as a countable union of this form, and minus infinity to B as, once again, a countable union of this form as well. Okay, this is certainly true, but it feels rather unmotivated, but we'll keep reading and hopefully come up with explanation. And T is closed under countable union. T is closed under countable union. We can conclude that T contains every open subset of R. Yeah, this is it true? Yeah, this is true. So basically, here we actually use the fact that every open subset of R is a countable union of open interval. So you see, open intervals in R can only take the form A to infinity, A to B, and minus B to infinity, minus infinity to B. So these are all the possible open intervals on R. And once we show that they're all in T, then their countable unions would be in T. And that's all there is to it for open subsets of R. So T contains every open subset of R. So T contains every open subset of, what does that mean? recall that Barreal sigma algebra is the smallest sigma algebra on R that contains all the open subsets. And T is a sigma algebra that contains all the open subsets. Therefore, T contains all the Barreal sigma algebra. Isn't that brilliant? Here, Wendelin says, from A to infinity, you can obtain all the intervals in R. From there, it's just the properties of preimages with union. Exactly. That's all there is to it. That's all there is to it. So we show that T is a sigma algebra, and then by the assumption, T contains A to infinity. T contains intervals of the form A to infinity, and then you can use the property of sigma algebra and some shenanigans with sets, basically with intervals. You can show that all open intervals, the only 3 forms of open intervals on R, they're all in T. Okay? Open intervals are all in T, therefore open sets are all in T. So T is a sigma algebra that contains all the open sets of R, but we know that Barreal sigma algebra is the smallest sigma algebra that contains all subsets of R. T contains the sigma algebra. So T contains the Barreal sigma algebra. So isn't that brilliant? Yes. So Wendelin nailed it. Thank you very much for summarizing the idea of the proof. Okay. The punchline of this paragraph is really just to show that T contains every open subset. Okay, so that's very cool. Okay, so just because I think we understood the proof pretty well, I'm not going to reproduce the proof on the spot. Okay, I'm going to continue moving forward. Hopefully we can do some exercise today. In the result above, we could replace the collection of the set A to infinity A and R by any collection of subsets of R such that the smallest sigma algebra containing that collection contains the Barreal sigma algebra of R. I believe you can replace this by minus infinity to B. Right, that would be the CDF. Right? That would be the CDF example I mentioned earlier. Because the CDF, the probability of x less than or equal to b, that's the CDF, which is denoted as fx of b in probability theory, is exactly the probability measure of the inverse image of the interval minus infinity to b. So if for every b minus infinity to b has its preimage in the sigma algebra S, x is a random variable. So the definition of random variable only requires that this probability is well defined, essentially. Okay, so that's it. For specific examples for such collection of subsets of R, see exercises 3 to 6. Okay, so that's pretty nice. So the overall philosophy of this proposition is that we wish to check measurability by looking at only the preimages of a very small collection of subsets and avoid working with Barreal sigma algebra directly. So if you can check f inverse of A to infinity is in S for every A, then it is implied that the inverse image of every Barreal subset is in S. So that's kind of nice. Right, so that's the idea. Anyway, so let's move on. We have been dealing with S measurable functions from X to R in the context of an arbitrary set and a sigma algebra S on X. An important special case of this setup is when X is a Barreal subset of R. Okay, X is a Barreal subset of R, and S is the set of Barreal subsets of R that are contained in S. Okay, so now imagine X is now a Barreal subset of R. Right. Previously we've been using X as an arbitrary set. And the sigma algebra is also the Barreau sigma algebra, but the Barreau sigma algebra of over big X, which is in itself a Barreau subset of R. See exercise 11 for another way of thinking about this sigma algebra. I think we'll have to do the exercises that Axler named because they serve a particular purpose. I'm not saying the other exercises are irrelevant, but we're going to prioritize these. Okay. Anyway, in this special case, the S measurable functions are called Barreau measurable. All right. Definition: the Barreau measurable function. Barreau measurable function says, suppose X is in R. X is a subset of R. A function f from X to R is called Barreau measurable if f inverse of B is a Barreau set for every Barreau set B in R. Okay, let's write that down. So that's a pretty important special case, I believe. And typically, let's say when you work with places like applied topic, for example, last week we did optimal control. And there was a constraint on so-called admissible control function. So basically a control function is a function of time. It takes value in the set of control parameters. So there we only said alpha, the control function is measurable. And because their time, 0 to infinity, is a subset of R, and it did not mention any other specific sigma algebra, it by default means Barreau measurable. Okay. Anyway, so here let's do this definition. I'll leave space for the previous proposition, which is very important actually. Here, let me just say definition 2.40. Definition. X is a subset of R. F from X to R is Barreau measurable. If F inverse B is a Barreau set, F inverse B is in the, I think you can write Barreau scripted B of X. That's a Barreau sigma algebra over X for all B in the Barreau sigma algebra of R. It's the same idea. It's the same idea. The pre-image or inverse image of measurable sets in the codomain is a member of the sigma algebra over the domain. So that's the idea. Okay, so that's the definition. If X is a subset of R, and there exists a Barreau measurable function f from X to R, then X must be a Barreau set. Yes, right? Because simply you can take R itself, because it works here. F inverse B is a Barreau set for every Barreau set B. Just take B to be R. Take B to be R. X equals F inverse of R. By the definition, that's a Barreau set, so X has to be a Barreau set. So this makes sense. This paragraph makes sense. Next up, if X is a subset of R, and F from X to R is a function, then F is Barreau measurable if and only if. Yeah. Why? Because we can use the previous argument. We can use the previous theorem, right? That's the proposition we used. You don't need to check F inverse B is a Barreau set for every Barreau set B. You just need to do that for a much smaller class of set A to infinity. or the semi-intervals of the form a to infinity. Yeah, this is correct. And now, suppose x is a set and f from x to r is a function. The measurability of f depends on the choice of a sigma algebra x. Exactly. Whenever we say something is measurable, we always fully means S measurable. We always have a choice of sigma algebra S. Although sometimes we don't mention it because it's clear from the context. Right? It depends on the choice of the sigma algebra S, obviously. Usually it's the Barreau set, but it can be different. Okay. Here, go ahead. Here it says, yeah, it depends on the choice of S. If the sigma algebra is called S, then we can discuss whether f is an S measurable function. If x is a Barreau subset of R, then S might be the set of Barreau sets containing X, in which case the phrase Barreau measurable means the same as S measurable. However, whether or not S is a collection of Barreau sets, we consider inverse images of Barreau subset of R when determining whether a function S is measurable. So the idea is, if the domain, the domain X can be may or may not be, may not even be a subset of R actually. It means that as long as the codomain is R, to determine measurability, we use Barreau sets in R. We always look at the inverse image of Barreau subset. That's what it's saying. Okay. The next result states that continuity interacts well with the notion of Barreau measurability. Okay, cool. Finally, we have some theorems on which kind of functions are Barreau measurable. It says every continuous real value function defined on the Barreau subset of R is Barreau measurable. So continuous functions are measurable. We usually just simplify the statement to mean this particular result. So that's pretty nice. So let's look at the proof. Here, I guess every continuous real value function defined on the Barreau subset of R. So let's say f is from x to R, x is Barreau, and the definition of measurability is very similar to the definition of continuity. It's similar to the definition of continuity in topology, right? Christian, I think that's what Christian is saying. The definition of continuity in topology says the inverse image of open sets is still open. The definition of measurability says the inverse image of a measurable set is measurable. Okay. In topology, in general topology, openness is defined as being a member of quote-unquote a topology, which is another collection of subsets. At some point, topology will interact with measure theory. But I see this using epsilon delta instead. And that works too, right? Because in metric space, epsilon delta is equivalent to the open set characterization. And open set characterization is also used in topology where you do not have a metric. Anyway, that's a digression. But basically, we don't want to make too much deviation from this particular theorem. Okay, so here we have this nice little fact that whenever you see a continuous function defined on the Barreau subset, then you immediately know that it's Barreau measurable. No more work is needed. Okay, so that's pretty cool. Suppose X is a subset in R, and f from X to R is continuous. So to prove that f is Barreau measurable, fix A in R. fixing, are we using, hold on a second, are we using 2.39? Right? I suppose we're checking whether the inverse image of a to infinity is in S, right? Yeah, this is kind of structural. I can kind of see this is what's happening. Okay. Structural preserving map in category theory. Okay. Yeah, indeed, we're looking at the inverse image of a to infinity. Right? So we wish to show that for every a, the inverse image of a to infinity is a Barreau sigma, is a Barreau, not a Barreau sigma, but a Barreau set in Bx. We want to show this is this. We want to show this is in Bx. This is what we want. Okay. So how does continuity comes into play? Right? We have to use the continuity assumption somehow. Right here, I think we're going to use the epsilon delta definition by the continuity of f. So here, f inverse of a to infinity. That's what? That's the collection of points x such that f of x is greater than a. So let's consider f of x greater than a. So if x is in big X and f of x is in a, f of x is greater than a, then what happens? Then there exists delta x such that fy is greater than a for all y in this open ball. Okay, basically open ball centered at x with radius delta. Let's draw a picture for that. So because f is continuous, here let's suppose a is here. F of x is greater than a here. So here let's say this is the threshold a, and f of x is greater than a. So this is x, for example, and this is f. Okay, the graph of f near x. The idea is if at the point x, the function f is greater than a, the points that are near x is also greater than a. It cannot change suddenly. You cannot say it's below a and suddenly at x it jumps over a. That violates continuity. Okay. There exists a delta x, a positive delta x, such that this is the idea that the points near x are also have their function value greater than a. So y, if let's say y is in this interval, x and plus or minus delta x, then fy is also greater than a. So this part of the graph, okay, is also greater than, so y is in here. So that's the idea. Okay, so we can write the inverse image as follows. So that's interesting. So we'll try to verify that. We'll verify that. Of course, we'll write the proof ourselves. So if this is the truth, if this is the case, okay, if this is the case, then what happened? Let's take this equation and see what the consequence of that. It says the union inside the large parentheses above is an open subset of R. Indeed, the big parentheses is a union of open intervals. And it is the fact from analysis or topology that arbitrary union of open sets is still open. This is an arbitrary union. This might not be countable, but it doesn't matter. It's the union of open sets which is always open. Okay. Hence, its intersection with X is a Barreau set. Exactly, because this is open, therefore Barreau. X is always Barreau. So the finite intersection is also Barreau, and we're done. Okay, so now it's just a matter of verifying this set equality. It all boils down to that. Okay, so let's write the proof ourselves. We need to verify this identity. This is the key to the whole proof. You see, we've been seeing this trickery a few times now. As Christian, the topological formulation would have been the more straightforward proof. Anyway, so here, you see, we use this trickery a lot down the road, actually. So that is to write a set as a union or intersection, and actually depend on what we want. Here, an arbitrary union already suffices. Sometimes you need a countable union, but that's the essence of the proof. All right, so this, even though this looks rather, it's really easy to check, right? Everything is easy to check, but this philosophy, this strategy needs to be internalized when we solve problems on our own. Okay, so anyway, let's write the proof for 2.41. I think this is worth writing. So theorem. I'm going to introduce notations. Okay, this way it's easier for me to prove things. Let X be a Borel subset of R. If f from X to R is continuous on X, then f is Borel measurable. All right. Yes, so basically this is what we want to prove. So let's start with the proof. Okay, by 2.39 suffices to show f inverse of a to infinity is Borel for all a in real. So to do that, let a be in real. Let's consider what this set is. Okay. Let a be in real. So suppose, actually, for each x in big X with f of x greater than a, the preimage of open is open. Thus, the function is measurable. But I honestly prefer doing yeah. Exactly, yeah. The topological proof would be just one line, but that's unfair for people who have never learned topology. Okay, so still, let's do the Axler way. Okay, for each x in big X with f of x greater than a, by continuity, there exists a delta of x such that f of y is greater than a, exists delta greater than 0 such that f of y is greater than a for whenever y is near x, basically x minus delta x plus delta x. Okay, that's cool. So that's the that's where we use continuity, and then we claim f inverse. You have this identity f inverse of a to infinity is the union. Okay, it is the union of x minus delta x plus delta x, such intervals such that, I guess, f of x greater than a, x such that f of x greater than a. intersect x. So once again, we want to put a picture on the side to remind ourselves what we're doing. Okay, so here this is a, the line a. Say x has value greater than a. This is delta x. This is a delta x neighborhood. Radius is delta x. So for every x, there exists such a neighborhood, and you just wanted to take the union. You want to take the union of all such. You want to take the union of all such little neighborhood of x. Right. So hang on. Let me just check actually. Yeah, this is correct. That's the same as x f of x such that x f of x is greater than a. Yeah, so it looks good. So now we need to prove this claim. To see this, proof of claim. Proof of claim. So so left to right, let x is in. So that's the one direction. Let x be in f inverse of a. F inverse from a to infinity. Oh, hi, Howinator. Thank you very much for joining the stream. F inverse of a to infinity. We want to show this is a. Want to show that this is a member of the set to the right. Okay, Howinator, just in case you're wondering what we're doing, we're trying to prove that continuous functions are measurable. It's also a nice exercise of the definition of continuity. So then f of x would be greater than a, obviously. We want to prove that x is in the set to the right. So clearly x is in big X. That's without question, because by the definition of inverse image, that's already implied. Okay, so not much to talk about. But now we need to show that it's in this union. So, since x satisfied f of x in f of x greater than a, then it is in its own interval. So since f of x is greater than a, x is in its own interval, x minus delta x, x plus delta x. So therefore it is in the union. So we're done. So this proves the, therefore you have the left to right direction, right? And then we do the other direction. So now let x be a member on the right. So that's a bit more complicated to write, but basically that's the union x from f of x greater than a, x minus delta x, x plus delta x, union of a bunch of open neighborhoods or open balls. We need to show that f of x is greater than a. Okay, f of x greater than a. Well, that just follows from the construction of delta x. So this just means that actually, you know what? Just to avoid confusion, let's put y here. Let's use a different notation. Say y. Actually, I'm not going to use y because y is typically the value of the function. Let's use xi, the Greek counterpart of x. Say xi is in this set, therefore xi is in x, xi is in big X, and xi is in one of the intervals. So xi is in x minus delta x, x plus delta x, for some x. For some x such that f of x is greater than a. But we know from the assumption, by the definition of delta x, if xi is in this interval, f xi must be greater than 0. By the definition, by our definition of delta x, you have f xi is greater than a. Not greater than 0, but greater than a. So this just means xi is in f inverse of a to infinity, which is the other direction. So you have the other direction as well, so we're done. So this proves the claim. So this proves the claim, then we can move on. So this is nice because here you have a union of open sets, which is open, therefore real, and intersect with x, which is always real. So the right-hand side, let's call this star, okay? Give it a name. Let's call this star. The right-hand side of star is real. Since x is real, and a union of open sets is open. A union of open sets is open and hence real. And of course, real sets are, the real sigma algebra is closed under countable intersection. And here you just need finite intersection. Anyway, so we're done. So by 2.39, this proves f is measurable, real measurable. Okay, so that's cool, we're done. Okay, even though verifying this identity is not hard, it's a good exercise in basic proof writing. Okay, this looks quite formidable for newcomers, but really it's just a basic element chasing argument. Anyway, let's continue. So now we have a shortcut, right? This theorem is a shortcut. Whenever you see a continuous function defined on a real subset, you know it is a real measurable function. So that's cool. Continue. Next, we come to another class of real measurable function. A similar definition could be made for decreasing functions with a corresponding similar result. So these are monotone functions. Definition, increasing function, strictly increasing. We all know what this means. Let x be a subset of R. F is from x to R. F is increasing if f of x less than or equal to f of y for x less than y. So this doesn't have to be strictly increasing. Okay. X is strictly less than y. F of x does not, it just only needs to be less than or equal to f of y. Okay. And if in the previous inequality, for f of x and f of y, you only have strict inequality, then you have strict increasing. All right, and the result says every increasing function is real measurable. Every increasing function is real measurable. Let's see how that works. It doesn't have to be continuous. It doesn't have to be continuous. It actually reminds me of the theory of Riemann integration. In the theory of Riemann integration, a continuous function over a closed and bounded interval is always Riemann integrable. And a monotone function is also Riemann integrable. But of course, the analogy is superficial. Okay, there's nothing essential going on here. Okay, just a nice symmetry here. Every increasing function is also Barreal measurable. Every increasing function defined under the Barreal subset of R is Barreal measurable. Let's continue. So, well, we're still going to use the shortcut. You see, 2.39 is proving to be very useful. Let X be a Barreal set. F is from X to R is increasing. To prove that F is Barreal measurable, what do we do? What do we do? So here we're using this little construction, which is quite nice. So first of all, fix A in R. We want to show that the F inverse of A to infinity is a Barreal subset. Okay, so that's what we want to do. Here, this is saying that let B be the infimum. Okay, so I guess perhaps it's good to draw a picture. So this is F, okay? I draw a continuous curve, but it doesn't have to be. It's just an increasing function. So let's suppose you have a cutoff point A on the y-axis. And this is what we mean by B. The infimum of the pre-image, or the inverse image A to infinity. This is B. That's the cutoff point. So that's B. And B, by the way, always exists. B always exists because the set A to infinity is bounded below. And since F is increasing, the inverse image is also bounded below. And every non-empty set, that is non-empty set of real numbers that is bounded below, has an infimum. That's a completeness axiom. So B is well defined. Okay, so here then it is easy to see. Okay, I guess we have to prove that formally. And it is easy to see that F inverse of A to infinity is B to infinity intersect X. Or there could be the other situation where B is a closed endpoint. That's also possible. You say, either way, we conclude that this is a Barreal set. So both are Barreal, so the intersection is Barreal. I guess we need to show that. Right? I guess we need to show that. Huh? So let's do that, and we'll move on to the next result. Okay. So here. (2.43) theorem. That's another useful criteria. Let's write it this way. Let X in R be Barreal. If F from X to R is increasing, in fact, you know what? Let's just write monotone. Is monotone. Then F is Barreal measurable. All right, let's start with the proof. So the proof, let's say we prove the case where F is increasing. The proof for the case where F is decreasing is similar. So that's what we want to do. Okay, by 2.39, it suffices to check for all A in real, F inverse of A to infinity is Barreal. This is what we want to do. Okay, so here its claim is, here's the claim. F inverse of a to infinity equals b to infinity intersect with x, or closed interval b to infinity intersect with x, where b is the infimum. Inverse a to infinity. Can we formally prove this? And of course, they can say, since both b to infinity and the closed interval are real, the result follows. Okay, so proof of claim. How do we do that? So B is infimum. I guess you need to use the definition of infimum. And by the way, when do you get an open interval and when do you get a closed interval? You can't use continuity anymore because f is not continuous. F is monotone. So you know what? Let x be in f inverse of the interval a to infinity for a start. Then f of x is greater than a. Then f of x is greater than a. So here do we know whether b is in x or not? We don't know, right? We don't know. We can't even say fb is greater than a. We can't say it because here we don't even know whether b is in the domain. So how can we use the symbol b? Right? We just need to show that x is greater or equal to b. Actually, you know what? That's enough. If x is in the set, then x is greater or equal to b. Then we're done. So we're done. X is in big X, that's without question. X is greater or equal to b, so it's it is either in this set or in this set, so we're done. So that's the proof of claim is literally one line. So where do we use monotone? Well, the monotonicity assumption, in particular, increasing the proof, the increasing assumption is used in the definition of B. Because f is increasing, f inverse of a to infinity is bounded below. Remark. Where did we use the assumption? Use the fact that f is increasing. Assumption. That f is increasing? Question mark? It's here. It's in the definition of B. And in particular, f inverse a to infinity is bounded below because f is increasing. B is included, depending on whether there's a jump. Yeah, exactly. It doesn't really matter. And actually, B is not even clear. It's not even clear whether B is in the domain. So you can't even say F experienced a jump at B, right? It doesn't matter. But so this is rather simple actually, because B is defined as the infimum of this set. If X is in the set, X has to be greater or equal to B. You're done. Increasing. Okay, so that's this proposition taken care of. Okay, 2.43 taken care of. And now let's take a look at composition. The next result shows that the measurability interacts well with composition. Cool. You see, here we have this little identity that we've shown earlier. So if X is XS is a measurable space, all right, and F from X to R is S measurable function, and G is a real valued but real measurable function defined on the subset of R and includes the range of F, and the composition is also measurable. So here, hold on a second. So this is X, this is R, and there's another copy of R. F is here, and imagine this is the range of F. This is the range of F. It's defined on a subset of R that includes the range. Okay, so the domain of G is a bit larger. Okay, the domain of G in itself is a bit larger, so this way composition makes sense. Okay, you first plug X into X and then plug F of X into G. Okay, I'll draw a nicer picture on the nodes. So this is a measurable function. Right, so we have this identity, 2.34. Well, starting from a Barreau set in R, that's the Barreau set on the R to the right end. Right, if that's a Barreau set, then by this identity, G inverse of B is Barreau. It's by the fact that G is Barreau measurable. And then F is also measurable, so we are done. Okay, so this is rather simple. Okay, let me just gonna draw a simple picture, and I will skip writing the proof on live. Okay. You see, I've accumulated a bunch of nodes. I should really upload these. Of course, these are all quote-unquote working progress nodes. Just in case that you don't have the appetite to watch the whole recording, but still want to see what we did, now you can go to the link and take a look at the notes. All right, so 2.44 has to do with composition of measurable function. So F from, okay, sorry, S is measurable space. F from X to R is S measurable. All right, and it says G. Why don't we write G is, give it a name, say Y, okay, Y to R. Y includes the range of X, or simply F of X, right, which is equivalent to F of X, image notation. Then the composition of F and G from X to R is as measurable. Is as measurable. So that's the statement. composition is measurable. Composition of measurable functions is measurable. So let's draw the diagram here. So here you have x. This is r. And this is another copy of r. All right, so this is f. And this is g. So the domain of g is, say, this part. Okay, this is y. This is y. G is from y to r. Okay, and here you have a piece of y, which is a range of x. So let's call this big F of x. This is big F of x, okay? And if, let's say, you have taken a real set B here, pull it back, the inverse image of the composition actually it does not have to be in the, hold on a second. Yeah, so what I'm saying is G inverse of B might be like this. It may not completely fall into fx. So this is G inverse of B. And now finally you take the F inverse here. You just care about this part. The F inverse of G inverse is this part. This belongs to the sigma algebra S. So that's the idea. Okay, so the key is to use 2.34, the inverse image identity. So this proves to be useful for this composition of measurable function. That's nice. Okay, cool. Let's move on. Here we have some examples. So if f is measurable, I guess this is a shortcut. Huh? Yeah, here it says if x and s is a measurable space, f from x to r is a measurable function, s measurable function, then 2.44 implies that the function minus f, half f, f absolute value, f squared are all measurable functions because they can be treated as compositions, right? It's composition with g, where g equals minus x, half x, x absolute value, and x squared. So that's pretty cool. Right. So these are, g are all continuous. All choices of g are continuous. And composition of measurable functions is still measurable. So that's nice. All right. Okay, cool. And now we have other properties. So this is very similar to elementary real analysis when you showed continuous function plus continuous function is still continuous, right? So here we're doing something similar. The sum of measurable functions, the difference between measurable functions, and the product of measurable functions are all measurable. And if g is non-zero, of course, f and g are both measurable. Okay, that's the assumption. If g is non-zero everywhere, then the ratio f over g is still measurable. Okay, so as expected, all the proofs makes heavy use of 2.39. So you just need to check the inverse image of a to infinity. But the proof is rather interesting. Once again, we make use of the shenanigan that you write a set as a countable union or some sort, as so to say, as a union of simpler sets. Union intersection of simpler sets. So let's see how that's done. Here, suppose A is in R. We will show that. First of all, you claim this identity. Okay, you claim this identity. The inverse image of f plus g. The inverse image of A to infinity under f plus g is the union. I suppose this R is a rational, huh? Is the union of all rationals. Why do we do that? Well, to cook up a countable union. That's how we use the closure under countable union problem. Okay? So it says it's the union over R in Q of the inverse image of R to infinity under G and intersection with the inverse image of A minus R to infinity under G. Right? So once you have that, then you're done. Because F inverse R to infinity, that's Borel. Actually, that's not Borel. This is in S. This is in S. Your G inverse is also in S. Intersection is in S, and then use closure under countable union, and you're done. So it boils down to showing this identity here. You see, this is hard to think about, right? This is not easy to somehow come up with this construction. We have to be mindful, like try to absorb these techniques, because this feels highly unnatural if you do it for the first time. Right. I think I mentioned something along the line in my measure theory made doable video a few months back, in which I use Axler's book and another book as recommended text. So I was saying, you probably need to study this stuff once every other day, because the construction is so unnatural. Right? Think about this. Like this is, I don't think this is very natural at all. The construction is so natural that if you leave this material for a long time and then you come back to it, it takes you roughly the same amount of time to pick up the material from scratch. You end up wasting your time. So, let's try to, I hate to use the word memorize, but try to internalize this sort of trickery. Right? I have no better motivation than saying, okay, we needed a countable union. Okay, so to prove 2.47, suppose x in the left-hand side. Once again, basic element chasing argument. So by this, we simply have a is less than f of x plus g of x. Okay, hold on a second. And then you just rearrange this inequality and write a minus f of x is less than g of x. So the interval, here Axler used a minus g of x less than f of x. So by this you got a minus g of x less than f of x, just a rearrangement. So this interval a minus g of x to f of x is non-empty. It's non-empty, therefore it contains some rational number. Of course, this rational number r is less than f of x. So x is in f inverse of r to infinity. And at the same time, the other interval a minus g of x is less than r. So x is in, you do the rearrangement again. So g of x is greater than a minus r. Right? So x is in the preimage of r minus r to infinity. So that's the that basically shows the this sort of this direction, So you start from an arbitrary element x in the left-hand side. You have proved that there exists an R such that x is in the intersection of f inverse r to infinity and g inverse r minus infinity. G inverse of r minus a minus r to infinity. So you showed one direction. You want to prove the other direction. So you assume there exists. Hold on a second. I mean, if you use R, what property do we use about Q? What property do we use about Q? Here we use the property Q, that is density. Right? The density of Q says if you have for any open interval, there must be a rational number in it. Right? That's so-called density of Q, that theorem. Okay? It's a basic fact in elementary analysis. Density of Q. Density of Q says if A and B are in R, and A is less than B, then there exists R in Q. Then there exists R in Q such that A is less than R less than B. This is density of Q. So here we use that. This is a consequence of the completeness axiom of R. All right. Oh, my goodness. Okay, so that's one direction, and the other direction is supposedly easier. Let's see why. In the other direction, suppose you have x is in the union, which means x is in f inverse blah 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 for some r in Q. Indeed, right? Once again, this is just basic proof writing. Okay, starting from a set is in an element in the union set, you can conclude that. So unpack that. I mean, it's the same work we did earlier. So it just means f of x is f of x is greater than r here, and g of x is greater than a minus r. There you go. And you add the two inequality, you get a is less than f of x plus g of x. So f plus g, this is f plus g, the new function f plus g of x. So therefore x is in the inverse image. So that's pretty cool. That's pretty cool. So you see, in the other direction, we never use that R is in Q. Right? It says some are in Q, but there's no property of Q that's being used here. In the first direction, the density of Q is used. So that's why the other direction is easier. Okay, so this proves f plus g is measurable. F minus g is easy because you already have f plus g. F minus g is just f plus minus g. But we know from earlier that if g is measurable, then minus g is also measurable. So f minus g is done. I expect multiplication is harder. But let's see. Ah, there's this trickery. My goodness, that's smart. This is smart. This is smart. Yo man, ceiling. Hi. Yeah, this is smart. This is so smart. I think Rudin used the same trick in baby Rudin to prove that f times g is integrable using the same identity. Such as coincidence that Q is dense is countable. Exactly, right? Exactly. So Q is dense is used for proving this identity. In particular, this inclusion here. And countable ensures countable union. Right? You want countable union, so this is in the scripture test. This is highly non-trivial. This proof, even though it looks rather innocuous, right? F and G are measurable. F plus G is measurable. This is actually, the construction is highly unnatural. This is highly unnatural. I mean, I gotta say, like, if I don't look at it, I can't do it from scratch. I don't know about you, but this looks to me highly unnatural. Okay, so yeah, try to accumulate this sort of unnatural technique so it becomes natural to you, right? So basically, it's like doing those epsilon delta proof. At a certain point, it just clicks. Right now, we're able to check this proof is correct, but perhaps it's still difficult for us to construct this sort of argument out of nothing, right? So this is very, I mean, what else can I say? This is very smart. Well, try to learn it and put that into your own arsenal. This kind of proof that makes sense that we live in a simulation. I know, right? It just feels unreal. This is so hard to come about. I don't know. Like, I don't know about you. Anyway, so here the product is once again is this is uses the polarization identity. So you know f and g are measurable. So f plus g is measurable, and the square is measurable. So you see these examples on random. Half minus squared. These aren't random. All right. Okay, so f plus g is f times g is measurable. It reminds me of the proof that Euclidean space is second countable. Yeah. Right. Exactly. Use rational coordinates. Right? Use rational coordinates and the radius that's also positive rational. It gives you a countable basis. I know, right? I don't know if we'll have time to talk about like the topological stuff in information geometry stream. I wanted to talk about so many things in there, but of course we have to make compromise. I don't want to deviate from the main subject matter too much, but once again, I cannot assume a lot of differential geometry background because yeah. Anyway, the proof for the product caught me off guard. Yeah, I know. This is too this is I don't know, this is too smart. What else can I say? Yeah, this is as I mentioned, this kind of, if I recall correctly, okay, in Baby Rudin, proving that if f and g are Riemann integrable, then their product is Riemann integrable, uses exactly the same trickery. All right. So anyway, let's move on to the final objective, namely division. Right? So to prove division is measurable, you just need the reciprocal is measurable. Right? So here, hold on. Suppose g is non-zero for all x in big X. The function defined on R minus 0, which is a Barreau subset, that's correct. Ah, smart. Okay, so once again, you use composition. Okay, since you're done. So 1 over x is continuous. 1 over g is measurable. This is so freaking smart. What else can I say? In particular, I think the first one. This is nothing short of miraculous. All right. What else? Okay, I'll defer writing the proof in my own notes. Let's take a look at the next one. Okay, because I really wanted to do some exercise ourselves. 2.48, limit of S measurable function. So this is interesting, right? We've been hammering the point of how Riemann integrable functions are poorly behaved under limit. Now we finally have a class of functions. We haven't even talked about integrals yet, but these are measurable functions. So measurable functions, they better behave well under limiting operations. They better be. Otherwise, this whole endeavor is kind of pointless, isn't it? So limit of S measurable function. Suppose you have a measurable space, and you have a sequence of S measurable function from X to R. So suppose the pointwise limit exists. Okay, so you fix x in big X and let k goes to infinity. That's the pointwise limit. Suppose the pointwise limit. So basically, we assume that the sequence converges pointwise. Then the pointwise limit is measurable. That's basically what it says. All right, so that's okay. You see, here comes this trickery again. This is so difficult to come about, right? This is, my goodness. How are we supposed to come up with this sort of construction? Let's be honest. Suppose A is in real. Of course, we wanted to verify f inverse of a to infinity is measurable, or is in S, right? So we try to use this sort of trickery. Because right now, we don't know the characteristics of, actually we do. We only know the sequence members are measurable. We know the sequence members are measurable. So, hold on a second. Here, we will show that the set on the left-hand side is the union j from 1 to infinity, union m from 1 to infinity, the intersection of k from infinity, m to infinity, of the inverse image fk inverse of a plus 1 over j to infinity. Okay, because each fk is measurable. So this set is in S, and you only have countable intersection and countable union, so it's in S. What on earth is this? Actually, guys, this reminds me, okay, at this point, this reminds me of the lim sup, lim inf. Limit superior, limit inferior. I forgot which one, but I think it's perhaps worth do a review on that, okay? But let's first read the proof, and then we will take this opportunity to review lim sup and lim inf. And actually, I think yesterday I made a question on lim sup, but for real numbers. Lim sup, lim inf generalizes beautifully to sequences of set, almost verbatim. All right, so here, okay, let's first let's suspend our amazement about this construction and just purely check whether this is true. To prove this identity, okay, how do we check this identity? To prove 2.49, first let's suppose x is in the inverse image. Sure, start from the left. Start from the left. Okay, what does that mean? Well, use the... So, okay, this just means that f of x is greater than a, no? F of x is greater than a. So use you're going to abuse Archimedean property. F of x is greater than a, so you're going to abuse Archimedean property. So this is f of x minus a greater than 0. So you can squeeze a 1 over j between 0 and f of x minus a. By Archimedean property, there exists a j such that f of x minus a is greater than 1 over j. And then you just rearrange, you get that. So this is abusing Archimedean property. The definition of limit, okay, the definition of limit, here we only have the pointwise limit. By fixing x, taking k to infinity. It says the definition of limit, the definition of the sequence of limit, now implies that there exists m in Z. okay, in Z such that, hold on a second, let's think about Y. Okay, let's write the definition of limit. What is the definition of limit? This is a classical analysis. Definition. Let AN be a sequence in real. AN, or just say this, the limit of AN is L. If for every epsilon greater than 0, there exists a big N such that whenever you have little n greater than big N, or greater or equal to big N, then AN minus L absolute value is less than epsilon. Right? So that's the definition of limit. Good old epsilon big N definition. So now what we have here, we have the assumption that for each fixed x, the limit of fkx is f of x. So this means for every epsilon greater than 0, there exists a big, let's exist m, so to say, little m, such that f of x, fk of x minus f of x is less than epsilon. That's what we wanted. Okay, so we're just going to use part of the inequality. That's the limit inferior, right? I think here is either limit in superior or limit inferior, but well, I'll do the review shortly after checking the proof by Axler. So the proof is not terribly long, right? So we want to use the definition of limit. So how do we do that? Well, from this inequality you would get, oh actually I didn't finish writing, such that whenever m is greater or equal to k, you have this, okay? And this inequality has actually it has two sides because it's absolute value inequality. So this implies f of x, fk of x is greater than f of x plus epsilon. Plus epsilon. But now what? You see the limit. How do we we have the limit is greater than a plus ij. Hold on a second. What is epsilon here? Is it a, or f of x is greater than a? F of x is greater than a plus ij. Probably a bit clearer, huh? Okay, so I think we gotta rewrite this ourselves. Thus x is in the right side. Hold on a second. Where is? Hold on a second. It's here. There exists a j such that f of x is greater than that. Right, for some m in z plus, such that for all k greater or equal to m. Okay. Okay, so yeah, I think this sentence needs a little bit of unpacking, but other than that, this paragraph is fine. To prove the other inclusion, suppose x in the right, suppose x is on the right here, you just want to show that x is satisfy f of x greater than the a. Right, there exists m and j, right? That's cool. M and j, yeah. Taking the limit, yeah, okay. Okay, this is easy to verify, but once again, coming up with this construction, it seems almost impossible, if I do say so that. Okay, so I think it's perhaps a good idea to review the notion of limit superior and limit inferior. Okay, here's the review. So let's first start from the definition of limit superior and limit inferior in R. Or sometimes called the upper and lower limit. Let's just content ourselves with considering bounded sequences, okay? Let AN be a bounded sequence. If AN is not bounded, if AN is, say, unbounded above, then lim sup of AN is just infinity. Lim sup and lim inf in general takes values in the extended real. But for our discussion, we're just going to let AN be a bounded sequence. AN be a bounded sequence. So there's that. So and if AN is bounded, and we're going to consider the case tail, the so-called case tail of AN. The so-called case tail of AN as the set defined, or let's use the as, hold on a second, as the set AK plus 1, AK plus 2, and so on. So AN is a sequence, right? So it's like A1, A2, A3, all these terms goes on forever. And just gonna chop off finitely many terms at the start and keep the tail. So the first tail is the whole set. The second tail is starting from A2 and everything after. So this should be clear. So this is a case tail of AN, defined as a set. You know what? Let's give it a name. Because the tail, let's call it TK. Give it a name called TK, where K is 1, 2, and so on. Right. So clearly, you have T1 contains T2, contains T3, and so on. So this is a nested sequence of sets. A nested sequence of sets. And let's recall a property of sup and inf. Recall properties. That is, if let A and B for subsets of R, A and B, for bounded sets A, B, and R, bounded sets A and B and R. I'm too sleepy to continue. Thank you, Gwendolyn, for joining the stream. Bye now. So for bounded sets A and B and R, if, say, A is a subset of B, then the supremum of A is no greater than the supremum of B. And the infimum of A is no less than the infimum of B. I think this should be pretty straightforward, right? Proving that should also be not that difficult, but I'm just going to use this property. So A is a subset of B. Imagine this is A and this is B. A is a subset of B. The sup of A should be less than or equal to the sup of B, and the inf of A should be greater or equal to the inf of B. Right? So therefore, because of this nested sequence of sets, so the sup of T1 should be greater than the sup of T2, greater than the sup of T3, and so on. And the inf of T1 should be less than or equal to the inf of T2, less than the inf of T3, and so on. So what this means is the sup of Tk is a decreasing sequence, i.e. the sup of Tk, which is the sup of, let's write Tk. Tk is the set of An such that n greater or equal to k. Sup of An where n is greater or equal to k. Right? This is decreasing. And what? And the inf of Tk, which is of course the inf of An, n greater or equal to k, is increasing. Hold on. Typo. Less than or equal to. Okay, this is increasing. And they are both bounded sequences because An is bounded. And what we know about bounded and monotone sequence, they converge. By the monotone sequence theorem in real analysis, if a sequence is bounded, say this is the upper and lower bound, if it is increasing, then it must converge. If it's decreasing, it also must converge. So these two sequences both have limit. So you can define them as your limit. Okay, so the limit of the sup of Tk therefore exists. K goes to infinity. And the lim, these are called lim sup and lim inf, basically. K goes to infinity, infimum of Tk also exists. By a monotone sequence theorem in analysis, in real analysis. Okay, monotone sequence theorem is just another statement for the what we call the completeness of R. So we're going to call these limits the lim sup and lim inf, obviously. So define. See, the notation is very suggestive. So define the lim sup of An as the lim k to infinity supremum of n greater or equal to k An, and lim inf of An as the limit k goes to infinity, the infimum of k greater or equal to k An. So that's the two definitions, lim sup and lim inf. Okay. So if we draw a picture, so in general, of course, a bounded sequence does not have a limit. Okay, so this is the, let's say this is the bound, upper bound. Here you have a lower bound. let's draw some points to illustrate the situation. So let's suppose you have a sequence that behaves this way. Okay, suppose this is your sequence. It does not converge. Imagine this is your sequence. So what we are doing here, this process, is imagine you're scanning through the sequence. So this is, let's say this is n greater or equal to k. And this is what we know as the tk, the case tail. Right? This is a case tail. As this threshold moves towards the right, as you can see, the supremum and infimum of the tail decreases and increases respectively. So here, you can see here, this is looks like how the supremum decays. Supremum of the tail decays. And now you here on the lower end, you got how the infimum of the lower bound goes up. Like so. All right, so that's the idea of lim sum and lim inf. If you look at the tail, if you look at the case tail, the set gets smaller and smaller as k increases. If the set gets smaller, the supremum gets smaller, the infimum gets larger. Right? So just we're going to squeeze the two bounds. And of course, if the two are the same, you can prove that the limit actually exists and is equal to the common value, which I'll not do here. Okay. My point is, here we only review the lim sum and lim inf in R. This works equally well, almost verbatim, for sequences of sets, of sequences of subset. Okay, so almost everything can be borrowed verbatim. So now, consider sets. Consider sequences of subsets. Okay, let big X be a set. Let big X be a set, and now we have a sequence, and say, let's just say AN. Okay, AN is a sequence, A1, A2, A3, and so on. Is a sequence of subsets of X. Subsets of X. So let's imagine. Okay, so you have this Venn diagram here, so to say. Perhaps I should draw it bigger, like this. Yeah, this is big X. And A1, A2 all the way to and all the way, they aren't necessarily nested or anything, right? This is A1, for example, this is A2. They can be rather general. A2 and so on. This is a sequence of subsets in X. So how do we come up with a notion of limit for this sequence, right? The question is, how do we define limit? The problem is, the usual epsilon big N definition cannot be incorporated here. Remember, to define notion of limit here, using the Cauchy's definition, right, the epsilon big N definition, you need a notion of distance. Basically, this absolute value sign here, the absolute value of AN minus L, that's the definition of a distance. So in general, to use the big epsilon and big N epsilon and big N definition, you need a notion of metric. But there's no natural metric to choose from. If now you just have a set, right? In order to discuss the notion of distance, you will have to come up with a notion of how to measure the distance, say, between two sets. And there's no canonical way to do that without introducing extra structures, right? Because X here, we don't even know if it's a metric space or not. So the epsilon big N definition is very awkward here. So instead, we consider a natural structure on sets, namely containment. That's an order relation. So we're going to pretty much assume, so not assume, but repeat the same process. So we're still going to consider the case tail. Consider the case tail. So the case tail would just be AK plus 1, and so on, where K is 1, 2, and so on. So that's the case tail. So that's the case tail. So we wish to come up with a notion of a soup and inf. Well, how do you take the soup of a bunch of sets? You take their union. So consider taking the union. The union of an, n greater or equal to k. We're going to call that the soup of an, n greater or equal to k. So just the tail taking the union. So that's the largest possible, so sorry, not the largest, that's the smallest actually. It's like the least upper bound, right? That's the smallest set that contains all the set here. Think about it. So the containment relation works like less than or equal to. Even the notation looks similar. So we're going to define the soup of a collection of sets to be their collective union, and of course the inf is defined as the intersection. Define the inf of a k as the intersection, n greater or equal to k, a k. All right, so these two are now defined, and now you can apply the same trickery and just let k goes to infinity. And let's think about, does that make sense? So first of all, here, define these two notions, the soup of the case tail and the inf of the case tail. So think about the monotonicity. Think of this as a sequence indexed by k. So for example, let's call it the sk, because that's a soup. Let's call it sk. And this is ik, inf, ik. Okay? Sk is what? As k gets larger, remember, as k gets larger, the number of sets taking part in the union gets smaller and smaller. Because the larger the k, the more finite terms are being removed from the sequence. So the union is a union of smaller number of sets, therefore it's smaller. So sk decreases. Sk decreases. So the idea is, if you want the union to be large, you want more sets, as many as possible. And if you want the intersection to be large, you pick fewer sets, right? So here, as k increases, fewer and fewer sets are taking the intersection, therefore ik is increasing. ik is increasing. And also here we don't even need the completeness axiom here. Sk and ik must have limit, because for a decreasing sequence of sets, its limit can just be defined as the intersection. So the limit of sk, as k tends to infinity, can simply be defined as the intersection of k greater or equal to 1 sk. So think about that. Sk is decreasing, meaning sk is nested in the sense that S1 contains S2 contains S3. Okay, ik is increasing in the sense that I1 is contained in I2, is contained in I3, and so on. Okay, so the limit of sk is just the intersection of all the sk, and the limit of ik, k to infinity, is just the union of all the iks, k greater or equal to 1. So putting everything together, we can define, this is just the limit of the soup of an. So limit of soup of n greater or equal to k, k tends to infinity. This is the intersection of the union. The intersection of k greater or equal to 0, and then union n greater or equal to k, an. Okay, so this is a motivated definition. And now here, the limit of ik is just the limit when k goes to infinity. The ik is the infimum of ak, k greater or equal to n, and that's the union out, intersection in the middle. Okay, so a quick way to remember this, okay, which order is which, is to use the real sequence analogy. So the lim sup is the limit of a decreasing sequence. The lim sup is the limit of a decreasing sequence, and lim inf is the limit of an increasing sequence. So here, because the outer operator is the intersection, it's decreasing. The outer operator's union is increasing. So here, based on this definition, let's take a look at Axler. So here, is this a lim inf or lim sup? I'm pretty sure this is not the only construction, because here the limit exists. It does not matter if you use lim sup or lim inf. And actually, this is a good illustration that perhaps in measure theory, lim sup and lim inf are more useful than limit, because the existence of limits often is not guaranteed. But lim sup and lim inf always exist. So I'm glad that we have this opportunity to review lim sup and lim inf. Here, you're taking the union, skipping this part, okay? Taking the union over m from 1 to infinity, and then intersection. That's lim inf. So somebody mentioned lim inf. Howanator mentioned lim inf. That's the lim inf. Folland did this proof a bit more explicitly. Thank you very much for mentioning that. You're completely right. Yeah, I just checked that. This is indeed lim inf. Union out, intersection in. Okay, so now imagine this. You're taking the lim inf of what? Hold on a second. So imagine fixing J. We're taking the lim inf of the inverse image of a plus 1 over j, as a sequence index k goes on to infinity. All right. So still not very easy to think about, huh? I think perhaps it's useful to recall a characterization of lim sup and lim inf. The lim sup of an can be described as the set of elements that appears in infinitely many values of n. Okay, so this is a little proposition. I believe that's correct. So what I'm saying is, okay, so this is just shortened to be the limit of lim sup of an. Okay, and this is just shortened to be the lim inf of an. Okay, so here the proposition says, if I recall correctly, the lim sup of an is the element x in big X such that x belongs to an for infinitely many values of n. For infinitely many values of n, the sanity check I like to do is to use lim inf is a subset. Yeah, that also works. So this is infinitely many values of n in big N. Okay, and second is the lim inf. The lim inf of an is the set of x in big X such that x in an for all but finitely many values. If I recall correctly, let's try to prove it. For all but finitely many. Because we could just verify the proof and move on, but I'm thinking whether there is a good way to motivate this identity, because I think for beginners it's extremely difficult to come up with this sort of construction for all but finitely many. Values of little n in big N. Right, so let's continue. So here, proof. Suppose x is in the lim sup of an, which is the same as the intersection of k greater or equal to 1, the union of n greater or equal to k, an. Okay, suppose that. And then what happened? Well, you get rid of the first intersection sign. That means x is in the union of an, n greater or equal to k, for all k equals 1, 2, and so on. There's that. Okay, there's that. So therefore, this means for each k in big N, there exists nk in big N such that, because x is in the union, so x actually not just in big N, it needs to be greater or equal to k. Okay, such that x is in a and k. Right? So that's a subsequence. This is a subsequence of A and K, this is a subsequence of the original sequence. This is a subsequence of the original sequence AN with the property that each element contains A. A and K contains X. So therefore, X is in AN for infinitely many values of N. Okay, so that direction is done. Okay, the other direction, suppose in probability theory we say AN infinitely often. In probability theory, okay, we say, but the interpretation doesn't matter. The interpretation holds in general set theory too. It does not only work in probability theory. Just that in probability theory, AN tends to be event. Okay, X in AN or omega in AN typically is written that way. Omega in AN means the event AN happens. So this just means AN infinitely often, happens infinitely many times, IO. So that's a shortcut in probability theory. So here, let's suppose AN infinitely often. Let's say X is in AN for infinitely many values of N, which means, well, it belongs to a subsequence. Okay, suppose X in AN for infinitely many values of N in big N. So there exists a sequence, a subsequence, A and K of AN such that A and K contains X for every X in sorry, not for every X, but for every K in big N. There exists a subsequence such that X is in A and K for every X in A and K. Okay, so cool. We have that. By the definition of subsequence, okay, by the definition of subsequence, A and K is greater or equal to K. That's baked in. That's baked in. So, yeah. So basically, this perhaps is a little bit more easy to forget. So basically, if you have, let's say, A1, A2, A3, and so on, the subsequence can be thought of as an express train. So think of this A1, A2, A3, and so on are train stations, train stops that just goes on forever. And now you wish to create an express route. How do you pick an express route? Well, you stop less frequently. So let's suppose you pick A1, A3, and so on. So A1 is now AN1. Okay, and A3 is AN2. Because A3 skips A2. N2 is greater than 3. So therefore, in general, the index nk for a subsequence A and K has this property. Nk is always greater or equal to K. Okay, by definition of subsequence, nk is greater or equal to K. So therefore, we have, X is in the, we want the union, X is in the A and K, which is a subset of the union K greater or equal to N. No, not K, N greater or equal to K. N greater or equal to K. AK. Because here, the sequence that takes part in the union contains AK, AK plus 1, and so on. Here, this is AK, AK plus 1, and so on taking the union, and NK is among them, because NK is greater or equal to K. And this is true for every K. So now you can take the intersection. That is to say, X is in the intersection. K from 1 to infinity. K greater or equal to 1. The union, N greater or equal to K. AK. Actually, AN. Sorry, my bad. No wonder this looks weird here. N. All right. Okay, so there's that. So this proves the other direction, and therefore 1 is proved. This proves 1. This proves 1, and now let's prove the other direction. Not the other direction, the other statement. What is lim_inf? Lim_inf also has an interpretation. This is the collection of elements in big X such that X is in AN for all but finite. All but finite means at certain index, say big N. Okay, it doesn't matter. It doesn't matter what happens before that index. What matters is after that index, as in X is in every single set AN, where little n is greater than big N. So in X is in A big N plus 1, X is in A big N plus 2, X is in A big N plus 3, and so on. All of them, all but finite. And that's what it means. So 3. So the second. Okay, let's prove that. So suppose X is in a lim_inf. If X is in lim_inf, then what happens? Let's use the definition, our definition for lim_inf, which is lim_inf is, as I mentioned, is a union of intersection. K greater or equal to 1 intersection. Because lim_inf is the limit of an increasing sequence. AN. All right? So, what does that mean? This means there exists K in big N such that X is in the intersection. But if it is in the intersection, that means it's in every one of them. Let's call this K star. Okay, let's call this K star. There exists a K star such that X is in the intersection of AN for all N greater or equal to K star. This is, of course, the same as saying there exists a K star in big N. X is in every single one of them. X belongs to all of AN. N equals K star plus 1, blah, blah, blah. All but finite. All but finitely many ANs. All right, so this is easy, and let's prove the other direction. If X is in the, other way around. I think it should be quite straightforward. Okay, if X, let X in AN for all but finite. That means X is in AN, N equals K star plus 1, and so on for some for some k star as an integer. Right? So yeah, suppose that. So it just means x is in the intersection. Okay, so there's really not much to talk about. And greater or equal to k star for some k star goes 1, 2, and so on. And of course, you take the union x. This just means if it's for some k star, then x is in the union. Okay, union k from 1 to infinity. Okay, or greater or equal to 1. And greater or equal to k an. So this proves 2. Okay, so not that hard to verify. Okay, so armed with this interpretation, it's now verified. And now armed with this interpretation, remember, we're taking the limit inferior. We're taking here, this is the limit inferior of the inverse image of a plus 1 over j infinity, a to infinity. So what is going on here? So let's suppose we fix k. Suppose we fix j. If we fix j, this whole thing contains of elements x, such that it contains all but finite. Sorry, it is in all but finitely many inverse images, fk inverse blah blah blah. So what does that mean? So what so for if we fix j, this is one of the tricky part, I think. So if you fix j, a plus 1 over j is a little bit higher. Is a little bit higher than a. Right? This function a is arbitrary constant. So a plus 1 over j is a little bit greater than j. And hold on a second. So the limit inferior contains x that appears in all but finitely many inverse images. And once you squeeze down, so let's say once you squeeze down this 1 over j to 0, right? You take j from 1 to infinity. J runs from 1 to infinity, so 1 over j tends to 0. 1 over j tends to 0. The set a plus 1 over j gets bigger. So the left-hand point moves towards the left. So that gets bigger. Right? That means the inverse image also gets bigger. So I'm saying is, now that the limit is taken, now that the limit of k goes to infinity is taken, with respect to the index j, as j increases, the set also increases. So this is also an increasing sequence. Of course, you take the union. Of course, that's an increasing sequence. Okay, you can verify this, but it's still hard to come up with a justification. Not a justification, but rather motivation to come up with this construction. That's what I'm saying. I guess first of all, I mean here the can we say something about this inverse image? The inverse image k inverse of a plus 1 over j to infinity. Can we say something about that? I guess it's bounded. I guess the you can say it's bounded because it converges pointwise. So all the all the images of fk is bounded, but that doesn't mean that the inverse image is bounded. No, that's not true. Well, but I mean it is bounded by x. That is bounded. I mean the set is always so there's no need to worry about that. So okay, so that's the limit inferior of fk inverse of a plus 1 over j. I guess my point is you can probably use limit superior too. You can probably use limit superior too. So here, if you use limit superior, if you use limit superior, that would be intersection on the outside, in the intersection in the middle, and union to the right. But in that case, it would be difficult to use the definition of limit. You see, the definition of limit says for all. You need for all k greater or equal to m. So therefore, in the third operation here, that's tailor-made for the definition of limit. I guess that's all you can say about that. I guess that's all you can say about it. You try to use the definition of limit. I guess that's about it. All right. Okay. So, oh well. But still, regardless, I mean, I did this review because limit superior, limit inferior will show up a lot later. Okay. For example, let's just take a look at a. I'm pretty sure let's just look at the index. Okay. Many results would require the limit superior, limit inferior, which I don't know. It feels to me that sometimes elementary analysis skip over lim sup lim inf. Maybe it's left as a homework exercise. But the lesson here is limit superior, limit inferior can be defined with only order structure involved. It does not need a metric structure. Whereas epsilon big N requires a metric structure. So it is a completely alternative way to define limit. And it's more general than limits, obviously. Here, I'm thinking about Fato's lemma. Where's F? Where's F? Okay, perhaps, hopefully this is the last theorem in the book. And after that, we'll do some exercise. So Fato's lemma 86. Wait, hold on a second. 86, that's just a... Yeah, here actually define it. So basically, this is actually pretty important. See, the Fato's lemma involves limit inferior. Here, yeah, actually define limit inferior. All right, so anyway, let's come to the, perhaps let's come to the main text here, measurable function. Is that the last result? It's not even the last result, huh? My goodness, there's still stuff going on. All right. So let's finish the last part, and hopefully we can do some exercise. In the last part, we deal with Borel subsets of extended real. Occasionally, we need to consider a function that takes values in minus infinity to positive infinity with closed endpoints. Okay, so recall in the very first stream, we discussed the notion of extended real, right? We reviewed the extended real. It's also in the, sorry, that's my video game. Okay, so that's basically here you have the extended real. It's just the regular real plus two symbols, okay, plus two extra symbols, minus infinity and positive infinity. And by considering these two extra symbols, the extended real is no longer a field because arithmetic is now only partially defined. Minus infinity plus infinity is undefined. For example, minus infinity divided by infinity is also undefined. So it loses the field structure, but it retains the order structure. Extended real is no longer a field. Arithmetic is only partially defined, but it retains the order structure. Infinity is greater than any real, and minus infinity is less than any real. All right, so we can extend the notion of real subsets to the subset of minus infinity to infinity. All right, a subset of minus infinity to infinity is called a Borel set if its intersection of R is a Borel set. Right? So if its intersection with R, by its very nature, would not include these two endpoints. Right? So in other words, if a set C is a Borel set, if and only if there exists a Borel set B and R, such as C is B or C is B union the infinite sign, B union the minus infinite sign, and so on. You should verify that with the definition above, the set of Borel subset of minus infinity to infinity is a sigma algebra on that. Okay, so we should do that. We should do that. You know what? Let's do that. Let's do that. It's okay if we don't finish the main text. It's important that we understand everything above. So we have, hold on. This is an interlude here. Let's write the definition. The definition of Borel subset. A subset of minus infinity to infinity is called a Borel set. If its intersection with R is Borel. Okay, so that is to say, that is C, which is a subset of minus infinity to infinity, is Borel if and only if there exists a Borel set in R such that C equals B or C equals B union positive infinity or C equals B union minus infinity or C equals B union the two infinities. There you go. So that's a Borel set in extended real. All right. So here you should verify with the definition above the set of Borel subsets is a sigma algebra. Is indeed a sigma algebra. All right. A proposition. The set of Borel sets in the extended real is a sigma algebra. We have proof. Let's go. first axiom, the extended real itself is a Barreau set. 1 is Barreau. Why? Because this set can be written as in the final form. That's just R union minus infinity and infinity. By definition, R is Barreau. R is in the usual Barreau of R. So we're good. Okay, and now we need to prove closeness under complement. So close under complement. Close under complement. All right, so let's say you have A, which is a subset of minus infinity to infinity. No, that's not what we wanted. We want X is a subset of minus infinity to infinity. That is Barreau. So use this definition. So you have a bunch of cases, right? So let's actually, you know what? Let's write that as C. So this is C. So you have 4 cases. So case 1. Case 1, C equals just B, where B is a Barreau subset of R. Then what? Then the complement extended real minus C would just be R minus C union the 2 endpoints, the 2 infinities. But because R minus C, this is in a regular Barreau. It's in the regular Barreau algebra, so Barreau sigma algebra. So this checks out, and you have 4 cases to check. Case 2, C equals B union positive infinity. B is Barreau. Popping up just now, what are we doing? Hi, yeah, I remember you, Guy Pirate. We're doing, we just, I think, yeah, we just finished the discussion on measurable set, measurable function. And now we're just finished discussing the notion of measurable function whose codomain is R. That is real valued measurable function. We just finished discussing that. And now we're extending that to function that takes extended real. So you can take an extra 2 notion, okay, extra 2 value, minus and positive infinity. So right now, just to say where we're at, we're in the second chapter, measure, near the end of the second section, called measurable spaces and function. We spend most of the time in today's stream discussing measurable function. And now we're extending all those notions, Barreau subsets, measurable functions, and whatnot to extended real. I hope I can do at least one exercise today. I'll close at 12. So see, as you can see right now, it's 10:48. So I hope I close at 12. But here, this is the rest of the main text, and then we have some exercises. And some of the exercises were mentioned in the main text, so we are going to prioritize them. All right, so here, let's continue verifying that the definition above is indeed a sigma algebra. All right, so here we have the second case. Here, C can be written as B union the symbol infinity. Okay, the symbol infinity. So, well, that just means the complement would be what? The complement Now the positive infinity sign is now removed, and there's no minus infinity sign, so this would be R minus B union with the minus infinity sign. Of course, hold on, I made a mistake here, so it should be B. R minus B, of course, is in the regular Babiro sigma algebra, so therefore it has the form a Babiro set in R union minus infinity. So we're good here. Yeah, case 3 is very similar to case 2. B union minus infinity. So you see, it's not that hard to check. It's very similar. Okay, I'm just going to quickly write this and move on to closure under countable union. Okay. And C is R minus B union positive infinity. All right. Case, and this is not case 2, this is case 3. Case 4. C is B union minus infinity to infinity, where B is a Babiro sigma Babiro set. All right, minus infinity to infinity. Minus C is what? Is R, just simply R minus B. So that's in the Babiro set of R. So it's closed under complement, so we're done. 3, closed under countable union. So let C1, C2, blah, 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 be subsets of the extended real that are real. So you get a sequence, okay? And you want to take their union and show this is still real. Okay, so, well, I mean, for each CI, they're of the 4 form. Right? The thing is, you can always write C as a partition. You can write every C as a partition. So you can write CI, so say CN as Bn union a finite set. Union a finite set, let's call it Fn, where Bn is in the Babiro sigma algebra of R, and Fn has 4 options, right? Fn can be empty, minus infinity. Actually, wouldn't it just be easier to say Fn is a subset of the 2 symbols, minus infinity and positive infinity? I spam clicked undo, so that's what happened. All right, so you can write it this way. So the union of Cn, n greater or equal to 1, would just be the union of Bn, n greater or equal to 1, and then the union of Fn, n greater or equal to 1. So the union of Bn, by definition, is in the Babiro sigma algebra of R. The union of Fn, well, the union of Fn can either be, well, there's this 4 value here. It's 0, not 0, but empty set, minus infinity, singleton, positive infinity, singleton, and minus infinity to infinity. There you go. So in each of these cases, this is a Babiro set in the extended sense. So we're done here. Okay, so this is not difficult to check. All right, so let's move on. Okay, so let's move on. Next, we extend the definition of S measurable function to functions taking values in minus infinity to infinity. All right, let's go on. A measurable function, the idea is the same, right? Here, you just have the extended real as the codomain, okay? And you want the inverse image or pre-image of a Borel subset in the extended real to be in the sigma algebra S. That's it. Okay. So now there's not much to talk about. The next result, which is analogous to 2.39, well, 2.39 allows us to check whether a function is measurable by only checking the pre-image, not all of a very small class of subsets of the Borel set. You don't need to check for every Borel set anymore. You just need to check semi-open interval, sorry, the semi-infinite interval. That would be enough. So this is very similar to 2.39. In 2.39, where we're dealing with Borel subsets of real, okay, without the infinity, the inverse image taken would be just be a to infinity, open interval. Here is a to infinity, closed interval. So it's very similar, right? So here it says, suppose you have a measurable space, xs, and f from x to the extended real, and it satisfies the inverse image of the interval a to infinity is in the sigma algebra S. For every a, then f is an S measurable function. Okay. The exercise is left to the reader, and also see exercise 27. We will do that exercise because this is so similar to 2.39. 2.39, as we mentioned, it also involves a lot of trickery. Okay, 2.39 was not an easy proposition. We end this section by showing that pointwise infimum. Okay, so here, does that look like a big theorem? Actually, it's not that long here, so this finishes up. So it says pointwise infimum and pointwise supremum is S measurable. So if you take a sequence that is S measurable, then the pointwise infimum and pointwise supremum is still measurable. So that's pretty nice. That's pretty nice. So why is that? Because in probability theory, often you want to take infimum and supremum of random variables. And it's good to know that the result is still random variables. All right, so let's see. So here you have X and S as a measurable space. F1, F2 all the way is a sequence of S measurable functions from X to the extended real. And next you define G and H as the so-called pointwise infimum and pointwise supremum. That is to say, if you fix X and take the supremum over K. Okay, take the supremum over all the K's. Can we maybe draw a picture of that, huh? Maybe draw a picture. So let's say here, this is big X, this is real, and you got a bunch of functions. Maybe like this. Okay, this is a bunch of functions, f1, f2, and so on. And now you fix X and take their supremum. So let's say supremum is here, infimum is here. That's the idea. And you do this for all the X. So imagine you scan from left to right. You do this for all the X, and you get the infimum function G, and you get the supremum function H. Okay, and the answer is that you have both functions f and g are S measurable. Okay, so the shenanigan we did earlier is still, you see, this is still, as we mentioned, the trickery. You want to construct a countable union. It almost always boils down to just countable union. Right, so you want to write the set that you wish to show is in the sigma algebra as a countable union. The definition of the supremum implies that, as you should verify. Let's go ahead and do that. Okay, so first write down the statement and then prove it. All right, Okay, so we need the definitions above, and then we'll leave the space for exercise, and we'll do that ourselves. Okay, this is definition 2.51 definition. X scripted as is measurable space. All right, f from big X to the extended real is S measurable. All right, if f inverse f inverse of B is in scripted S for all. For all B, that is for real. Okay, that's the definition. And then 2.52 is a theorem which says you have the same setup. Okay, X, S as a measurable space. F from X to minus infinity to infinity satisfies F inverse of A to infinity closed interval. Okay, do you want to make that super obvious? This is a closed interval is in S. If that's true for all A in big R, then you have F is S measurable. Okay, so I think we will definitely do exercise 27. Proof is exercise 27, along with some previously mentioned exercises. Okay, we'll do as many as possible in the time remains. Okay, here you have a theorem 2.53 which says xs given xs blah blah blah. All right. Here, suppose if let's say if f1 f2 and so on are S measurable function, okay, from X to extended real, are going to define then g of x is defined as the infimum of fk of x, k equals 1, 2, and so on. Hk, which is defined as the supremum of fk of x, k equals 1, 2, and so on. So these two functions are also S measurable. Okay, very useful result for probability theory. Okay. And by the way, I just want to briefly remark that. Okay, what we mentioned, what we did today. One of these results, algebraic operations with measurable functions. This shows that measurable functions forms a vector space. first of all, addition is closed. Addition is closed, and also here, I mean, it doesn't matter. Here we say half. That's to say a constant multiple of a measurable function is measurable. So combined with addition is closed, measurable functions form a vector space. So bear that in mind. Okay, so that's cool. Okay, it's not obvious. Okay, it's not obvious at all, because remember how hard it took us to prove that addition is closed. You need to come up with this weird construction. Okay. So I just want to remark that overall we have seen that measurable functions form a vector space. All right. So coming back to the proof of the last proposition. All right. So here, I want to show that the H inverse, the inverse image of A to infinity, H is the infimum. Okay, so, all right, so here, I guess claim, proof, claim, for every A in R, we have the following. It says, by the definition of supremum, we should have this. So H inverse of A to infinity is the union, K from 1 to infinity, Fk inverse from A to infinity. Okay, so that's the claim. Okay, so anyway, let's move on. Want to prove that. To see this, okay, let x in first, let x in H inverse of A to infinity. I want to show it's on the right hand side as well. Well, this just means that H of x is greater than A. Right? It just means that H of x is greater than A. Since hold on a second. Since can use the definition of H is a supremum. Since H of x is the supremum of f of k, fk of x, k equals 1, 2, and so on. Since h of x is the sup, that means h of x is greater than every one of them, right? Hold on. H is the sup here. H is a sup, then what happens? H of x is greater or equal to fk of x for all k. Then why the union? No? So here, imagine what we're trying to show here. We're trying to show x is in one of those sets to prove this is a union. You know what? Let me insert that sentence here. Okay? Perhaps we need a contradiction. Let's go. Perhaps. Okay? So need to show x is in fk f inverse k a to infinity. Need to show that for at least one k, for some k. equals 1, 2, and so on. i.e., which is the same as fk of x is greater than a for some k equals 1, 2, and so on, right? So we need to show that. We need to show f of x is greater than k. So here we have h of x is greater than k. So imagine this, right? So imagine this. So you have, okay, so let's draw a line segment here. So this is a, h is here, h of x is here. H of x I know is greater than all of the f of x. So imagine if all of the fk's are to the left of a. Let's say f1, f2, blah blah blah, fx1, fx2, and all are here. If for contradiction, then that means h of x is not the least upper bound. So you can squeeze h of x a little bit to the left. Remember, supremum is the least upper bound. So maybe we don't need a contradiction, but just say h of x is greater than a. Then you can, because this is the least upper bound, then hx minus h of x minus, say, what's the gap between them? The gap is h of x minus a. So you can pick a midpoint here. That would be h of x plus a over 2. This is not a, this is not a an upper bound. So one of the fk's should be greater here. Fk of x should be greater than here, so it has to be greater than a. So that's the idea. All right. So that's the picture. All right. So here, since you have the supremum assumption, the supremum assumption and h of x is greater than a, we have h of x greater than a, and hence a is less than h of x plus a over 2 over h of x. H of x. So the idea is, therefore, h of x plus a over 2, this is not a sup. This is not, actually, it's not a sup. It's not a lower, it's not an upper bound. It's not an upper bound of fk of x, k, blah blah blah. All right, so there's that. It's not an upper bound. So therefore, there exists k. There exists k equals 1, 2, and so on, so that fk of x is greater, strictly greater than h of x plus a over 2, which is greater than a. So this is exactly what we needed. As needed, okay? So also on the right-hand side, also, if we let x to be one of the things on the right, if let x to be in the union k goes from 1 to infinity, f inverse k. You see, working with inverse images is something that we need to be extremely proficient to deal with measures theory. Okay, working with inverse image is not something that we typically do elsewhere. I don't think, right? So I guess this is just the unnaturalness of working with inverse images in general. Okay, draw as many Venn diagrams as you can possibly can to help build intuition. So there you go. So let x to be in the union. This means there exists some k in 1, 2, and so on, so that x is in the inverse image of a to infinity under fk. All right. So this just means that fk of x is greater than a for that k, for that particular k. And since h is a soup, since h is the soup of fk, is greater or equal to f of k. Right. You have h of x is greater equal to f of fk of x, which is greater than a, i.e. h of x greater than a just means x is in the inverse image of a to infinity. So we're done. So this proves the claim. All right, so this proves the claim. So therefore, here you're done, right? By the it immediately follows, right? You have the, if you have this claim, then this immediately shows that h is measurable. Okay, h is as measurable, and now to do the infimum, well, infimum you can do the flip sign trick. The infimum is what? G of x. What is g of x? Well, you can, take the double negative. G of x is the negative supremum of negative f of k, so you're done. Each minus f of k is measurable. So the infimum is also measurable. So this is really straightforward. Let's just write that down. So here you have finish this up, and we'll do exercises, okay? As promised. Take, write the hell? Okay, write g of x, which is the infimum of fkx, where k is 1, 2, and so on, as the negative supremum of minus fkx. K is 1, 2, and so on. Right, g of x as such, this shows that g is measurable as well. Okay, so we're done. Okay, there you go. That's this proof, and we have a bunch of exercises that needs to be addressed. So according to what's mentioned in the main text, so let's highlight them. Okay, so we already seen exercise 27 is mentioned, so that's a priority. Lots of questions, lots of exercises. Hold on, 27? Give a counterexample. What the hell? I thought 27 was to prove the statement, huh? Okay, cool. That's an exercise that needs to be worried about, and here we also need to worry about a few things. Okay, going back, I remember seeing a few exercise mentioned there. Exercise 11, yeah, exercise 11 and 3 to 6. So those are the exercises being mentioned in the main text, so let's go over them. 3 to 6, 11, and 27. We'll see how we do, how well we do. Okay, once again, there's no rush. Just slow and steady wins the race. 3, 4, 5, 6, 11. All right, let's go. Exercise 2b. Suppose S is the smallest sigma algebra on R containing the smallest sigma algebra. Right, that's the smallest sigma algebra. The smallest sigma algebra on R containing the form R to S, left open, right closed, where R and S are rationals. Prove that S is a collection of Borel subsets. So this is the same as a Borel subset. This is the smallest sigma algebra containing this. How do we? What would be the strategy here? It is equal. It is the same as the Borel subset. So Borel subsets. The whole point is that Borel subsets can be described in many ways. Right? In the definition, Borel subsets is the smallest sigma algebra containing all the open sets. And here we say that this is the smallest sigma algebra containing minus R to S. What would be the strategy to prove this? This is the smallest sigma algebra containing minus R to S. Sorry, R to S. R is a rational. So some sort of countable union business has to be done, huh? What we can show is, every open set can be formed using a complement and countable union using this. So that means the open sets are the open sets on R are in here. So that means this is a sigma algebra. This is a sigma algebra that contains open set. But still we need to show this is the smallest. What I just described is showing that the Borel sigma algebra is a subset of S. Is there any hints in the main text there? Because I can't remember. In the result above, we could replace the collection of minus of a to infinity by any collection of subsets R such that the smallest sigma algebra containing that collection. Hold on a second. In the result above, that's 2.39. The 2.39 says in the result above, we could replace the collection of sets a to infinity, a is in real, by any collection of subsets of R such that the smallest sigma algebra containing that collection contains the real subset of R. For specific examples of such collection, okay, say C. Okay, there's no hint there. That's fine. Okay. What would be the general strategy here? It's not hard to show every open set can be written as complements or countable union. In fact, countable union should be enough. Countable union of this form. But how do you say show that this is the smallest, huh? Because we're running a little bit short on time, I'm going to seek help from AI. Okay, so hold on a second, let me. Okay, because I just need the opposite direction, right? So let's go and see. So let me just ask a general question. So so given a collection of subsets of R, how would we proceed so given a subset of R to show the collection, let's call it C, to show C is the smallest, no, to show the smallest sigma algebra containing C is the real sigma algebra. How do we do that in general? It's like, you know, in elementary analysis, when you want to show a set has a sup equals something, right? It's usually easy to show the sup is an upper bound. It's the least upper bound part. That's the difficult part. Right? To show the smallest sigma algebra containing C is this real sigma algebra. How should we proceed in general? There is a very standard strategy for these problems. The idea is to prove two inclusion. All right. So suppose the family C, denote that. So to prove this, okay. So first you show. Hold on a second. To show. Actually, you know what? I thought the opposite was easy. I thought the opposite was easy, right? So here it says the sigma algebra contains C. The smallest sigma algebra contains C is a subset of R. I thought this is hard, but okay, this is actually the easy one. How come? is that to show every set in C is real. Okay, since itself is a sigma algebra. Yeah, this is a sigma algebra. Ah, right. Oh, well, okay. Because every set here, you see, every set here, R to S, that's a real set. This is a real set. Every one of these sets is a real set. Then think about why is that? By the minimality of right. I see. So BR is a sigma algebra. BR is a sigma algebra and it contains all of this. So yeah. Okay. Actually, here this is where the works lie. Okay. Okay. I missed the first direction actually. I must actually here. You see, this is how simple is that. I forgot this is a real set. Okay. I think now we can go ahead and write it up. Okay. So there you go. That's a general strategy. Exercise 2B. Exercise 2B is 3. What are the prerequisites to learn this? Elementary analysis? Elementary analysis, so you need to, if you've seen a book called Understanding Analysis by Abbott, that's a good place to start. By S. Abbott. So yeah, what is a prerequisite? So it's the most important skill, I think, overall, is not really the content of analysis, but rather proof writing skill. The ability to work with sets, functions, equivalent class, that sort of thing. Okay, and actually, you know what? Yeah, I mentioned this a couple of times. I'm in high school. Okay, wow. Oh, you're in high school, then this is graduate school stuff. Okay, bro. This is typically speaking uh, last year undergraduate or beginning graduate stuff. But still, if you wanted to learn this, first, actually, learn proof-based math. Okay, learn proof-based mathematics. And I will, okay, I will put it in chat. I will make a live probably next week on this. Probably is going to be a few streams on that because you can't do that in just 4 hours. It's impossible. On basics of proof writing. That's it. Basics of set theoretic. Okay, set theory proofs and etc. Because that's the bare minimum to study this. Okay, and yeah, we'll cover things like set, functions, equivalence classes, cardinality, the definition of real numbers, that sort of thing. Okay, and this is really not just for this particular subject, it's pretty much all of advanced math. Okay, and if you're in high school, understandably, this is very difficult. This is even difficult for beginning PhD students. Anyway, so here, I'm just going to write it this way. But I'm glad you to tune in and ask for the prerequisite. So, Sandra will try and learn some proof writing. Yes, that would be the best place to start. Okay, so yeah, S is denoted as the smallest sigma algebra. On R containing RS interval of this form, where R and S are both rationals. Yeah, I made a poll this week asking whether people like the idea of a live stream on the basics of proof writing, basically the prerequisite of this stuff. And what's interesting is that almost exactly 80% people answered yes, and 20%, of course, that's not a big sample size compared to the subscriber base, but overall, among those who responded, 40%, not 40%, 80% said yes. So I guess that's a strong case to do that. Okay. So just a little bit of a overall positioning of the channel. I think it's fair to say that so far most of the stuff that we cover on the channel are like advanced undergraduate / graduate stuff. But that being said, I do post like quizzes on my community tab daily, actually, on the more fundamentals. So the fundamentals include calculus, linear algebra, basic proof writing skills, probability, basic probability, non-measure theoretic probability, and some real analysis. That's the selection range. I try to keep the questions within that range, which of course already has a lot of stuff to cover. So that's basically you can argue the prerequisite, overall the prerequisites for most of the stuff on the channel. But of course, individual topics vary. Okay, so anyway, prove that S equals the Barrio R. Okay, proof. Okay. First let's prove that S is contained in the Barrio of R. A book of proof is very good. Yeah, book of proof is indeed very good. But for my live stream, because of a time constraint, I'm going to use actually the first chapter of Moncrief's topology. So I will type in chat. I will, with the intro to proof live, I will use chapter 1 of topology by Moncrief. Okay. The nice thing about Moncrief is that there are a lot of exercises throughout the book, including some very elementary ones. So I think that's a good progression. Okay, and just to keep both beginners and veterans interested, we're going to see how those basic techniques leads to the proof of the existence of non-measurable sets. So it just makes use of all the things that I just mentioned: set, functions, equivalence classes, cardinality, axiom of choice also. So you see, using all these tools, you can get extremely complicated, non-intuitive things. Right? So it's just because usually when it comes to studying introduction to proofs, it feels like you're just spending a lot of time proving quote-unquote trivial stuff that is obvious, but it's important for a reason, because the complicated things are for the most of the part, just a mastery of the elementary ones. Okay, so you should be able to do like basic proof writing as if it were second nature, because this way the difficulty of proof writing itself, when being coupled with the difficulty of the material, is very discouraging sometimes. But anyway, let's come back to the proof. Okay, so first let's show the direction that S is a subset of BR. So yeah, like this. So let's do that. And this is very easy. First of all, BR is a sigma algebra, and every set of the form every set R of the form RS, let's say for every, so first of all, for every RS in Q, for all RS, this is in real R. Actually, that's not a good way to write it. Actually, yeah, that's okay, that's fine. Or you can write this collection is a subset of BR. That works too. It's the same meaning. Okay, no harm is done here. And BR is itself a sigma algebra. So this is a sigma algebra that contains all these sets. So by the minimality of S is contained in BR. So that's with the first direction done, and the opposite direction. The opposite direction is done in that way. So as I was saying, you wanted to show that every open set is contained in S. Okay, so and to do that, we're going to show three kinds of open intervals. Three kinds of open intervals are countable unions of as such. So okay, let A be in real. Okay, let A and B be in real. Okay, so we will show that I have a PhD in math. Why am I here? Well, I don't know. You tell me. like, have you taken measure theory, if I may ask? If you have experience with measure theory or whatnot, please feel free to share your experience. I mean, I don't have a PhD, so you're probably more knowledgeable than me. So we show that A to infinity minus infinity B and A less than B. Of course, that's great. That's awesome. Thank you so much. I probably need your advice on this. Okay, that's great. Awesome. Thanks for joining the stream. Thank you, Dylan. So, and you can check my proof and you can comment on like my approach and whatnot. I mean, well, I cheated a little bit. Well, the first direction was in fact suggested by AI. Okay, so we show that A to infinity minus infinity to B and AB. Okay, of course, assuming here in the last case, assuming A is less than B. In the last situation, you're assuming A is less than B are all in S. Okay? So if that's done, then once that's shown, it follows that any open set in R is in S, because any open set in R is just a countable union of intervals like these. Okay, this will imply that any open set in R is in S. This will imply that any open set is in S, and S is a sigma algebra. Right? This S is a sigma algebra, so this is a sigma algebra that contains all open sets in S, and i.e. By the minimality of BR, okay, this with the minimality of BR implies Dylan, by the way, if you don't mind, which area of probability do you work in? I'm just curious, actually, but it's okay. You don't have to share or anything. I'm just curious because implies BRS is in BR is in S. So this way, and then you're done. So okay, so it all amounts to showing this. All right. Okay. So A let how do I do that? Well, you can use the fact that rational is dense. So there exists a rational sequence that converges to A. So for A to infinity, you can use the fact that yeah, you can for A is in for let for A to infinity, let say RK be a sequence in Q such that RK decreases and it converges to A. So this notation means RK decreases and it converges to A. Okay, so let me draw a picture here. So this is A to infinity. Oh, actually here we need a right endpoint, huh? We need a right endpoint. Oh, well, then that's fine. I'm just going to use, there's no need to do that. Let me just, here, there's no need to do that. Okay, so for A to infinity, you just take, oh, actually you do. A is a real, it's not a rational. A isn't a real, not a rational. So, well, let's see. So this is A to infinity. Maybe we can pick a, yeah, RK. Yeah, okay, everything is still correct. I mean, I take that back. So RK, let RK be a sequence in Q, but you need a right endpoint. So the right endpoint, let's just pick K. Okay, RK be a sequence in Q with the property RK decreases to A. Okay, and then we have A to infinity, A to infinity equals the union of RK and K, because K tends to infinity. So RK and K is an element of this form, R to S, K greater or equal to 1. As K tends to infinity, RK approaches A, and yeah, there you go. So right, so there's that. So this proves A to infinity is in S. Okay, and then let's do minus infinity to B. Minus infinity to B, to do that, it's similar to the other way. Well, let's say SK be a sequence in Q with SK goes up to B. sk goes up to b. So there you go. That's the illustration. You have minus infinity to b. We want this interval. So you need the upper limit to approach b, and say this is minus k. So therefore you can write minus infinity to b, okay, as the union k greater or equal to 1 minus infinity rk. Oh no, minus infinity is not allowed because the endpoint here should be finite. That's no problem. So just do minus k here. Minus k, not rk, but sk. Okay, and that's also in scripted S. All right. Okay, so that's done. And lastly, well, you just need to take the intersection of a to infinity and b to the minus infinity to b. So when a is less than b, a to b open interval is simply the intersection of minus infinity to b and a to infinity. All right, so there's that. So this is also in S. So overall, we're done. Okay, so that's exercise 3. Okay, now because we don't have an awful lot of time left, I think for 3, 4, 5, the strategies are similar. So first of all, the first direction is entirely the same because every one of these sets are Borel sets. It's all Borel sets. So you just need to show that the open sets can be approximated using countable union and whatnot using these sets. Okay, and for that I'm going to take a look at, okay, why is 11 mentioned? Hang on a second. Why is 11 mentioned? "11" is mentioned right here. Important special case of this setup is when x is okay. So exercise 11, for another way of thinking about this sigma algebra. Okay, this sigma algebra. The sigma algebra here is XS, where X is a Borel subset of R, and S is a set of Borel subset of R that are contained in X. Got it. Okay, 11. Okay, 11. This is important. And let's go check that out. You know what? I'm just gonna copy the question here, so save me some writing. All right. So I want to show that T is a sigma algebra because it's actually a general setting. Okay, nothing to do with Borel sigma algebra. So T is a sigma algebra on the set Y, and X is a subset of T. Sorry, not a subset. X is in T. Okay, X is an element of the sigma algebra T, scripted T. So now you have S. S is the collection of the set E, which are in T, such that E is a subset of big X. So imagine this. So let's draw a diagram here. So in general, you got a big set Y and a sigma algebra associated with it, to T. And now look at that. So here you have E. Actually, okay, here you have X. Actually, X is a subset of Y. This is X. X is in scripted T, a sigma algebra. And now we're looking at scripted S. Scripted S is the collection of subset of X. So it's even smaller. This is even smaller, and say here you have a set E. Okay, E is a subset of X and is in T, and want to show that S equals F intersect with X such that F is in T, and finally show that S is a sigma algebra. Let's go. Okay, proof. Starting from the definition. Okay, this is a definition of S. So okay, let E be in scripted S. Therefore, E is in scripted T, sigma algebra, and also E is a subset of X. Is a subset of X. All right. Want to show that. Need to show. Actually, this is a first direction. Need to show. Need to show here E equals F intersect big X for some F in scripted T. No, why do I write scripted F? This is what we want. This is what we want. So here, think about that. How do we go about showing that? E is in T. E is in T. E is a subset of X. T is a sigma algebra. Y is so you have this collection of subset T on the second set Y. X is in scripted T, and X is in scripted T, and S has the form. I want to show X has the form F intersect X. So the visual should be something like this. So imagine you have another set F in scripted T, and the intersection of F and X, that's E. That's what we wanted. Scripted T is a sigma algebra on the set Y, and big X is in T. Well, could we just write, hang on, F is F, we need to construct an F in scripted. There's so little thing to work with. That's the thing, right? So you have a sigma algebra T, but there's not much said about it. So you have a sigma algebra T, and S is defined as the members of T that are contained in X. So what the question is saying, S can also be thought of as the result of intersection of x time x and x, f and x, where f runs over all the sets in the sigma algebra. So here I'm having a little bit of a trouble showing one inclusion. So why don't we try the other? So if let's say let f be in not scripted f. Okay, my bad. Just let f in scripted t. At f in scripted t, you need to show f intersect x is in as defined in as such. So that is to show f intersect x is in T. Yeah, this is in T. And f intersect x is contained in X. Well, that's obvious. That's obvious because, well, T is in T contains big X. F is in big T. Sorry, big T. My goodness, I can't even say things correctly. So basically, here X is a set in big T, and we assume that F is a set in big T. Sigma algebra is closed under intersection, so we're done here. So we're basically done. Okay, so let F in scripted T, since X is in scripted T, we have the intersections in T. And of course, as usual, as always, hi there, hi Matthew. And of course, the intersection of f and x is contained in X. So this way, we can say the set of, hold on a second, the set of f intersect x such that f is in scripted T. Good job, I suppose. Thank you very much for your support. Yeah, I'm so grateful for the support because it's quite incredible that the first episode of the series has over like 10,000 views or something, which is kind of insane to think about. Like, who would watch a guy do math for over 4 hours? I'm just like, this is like, I'm just doing, if I don't do the live stream, this is how I study. I just added the extra work of talking to the screen, which I normally do that anyway. So, thank you so much. So here you have the intersection that I'm trying to say is the intersection f intersect x, where f runs from scripted T, is a subset of S to satisfy all these conditions. But the converse direction seems to be harder. Okay, so in the other direction, you start from an arbitrary point, not an arbitrary point, arbitrary E in S. Okay, wow, so you're studying through live, that's great. I mean, let's be honest, I'm not a complete beginner when it comes to this stuff, but a lot of details I can't remember. And I'm doing this not because I have some exams to prepare, because I don't. It's just for the sake of relearning this stuff, hopefully to get a deeper understanding. So really, I'm grateful that I even have a following of this. So just happens, I guess, I hope this is also helpful to others, but mostly it's just I'm doing this for myself. Anyway, thank you very much. No, you're not annoying me. Actually, a welcome question. Actually, one of the reason I decided to go live is because I have this great community that people point out my mistake when I'm doing it. You see, how rare is that? You know, one of the most difficult thing when you study math is to get feedback, and I get feedbacks for free. like, so go ahead and say, like, if you don't understand something, say it. Okay, it's likely that I'm very likely to make mistakes, and if I don't understand something, I'll say it out loud too. So, yeah. Anyway, so here the opposite direction. I got stuck over there, right? So I said let E to be in S. Let E to be in S, which means E is an element in T and E is contained in X. So we wanted to show that E is the result of some sort of intersection. Is a result of some sort of intersection. Well, I guess you can just pick F to be E. Right? Because E is in T. So actually the reason I got stuck is actually really stupid. There's really not much to it. Okay, let E be in S, that just means E is in scripted T and E is contained in X. And you can simply write E as the intersection of E intersect X. E is a subset of X, so this holds. So therefore, E is in the set F intersect X such that F is in T. So basically here I'm picking E to be F here. So there you go. E is in T, so F is in T. So A is done. So it's actually really silly. That's part A. And part B, we want to show that S is a sigma algebra. All right, so to show the sigma algebra, it checks three things. First one you need to show X itself is in S. X itself is in S. Can we see that? Of course, because X is in T and X itself is containing X. This is clear. Since X is in T, that's given, and X is contained in X. Easy. All right, let's continue. So second, you need to show S is closed under a complement. S is closed under complement. So let say E is in S. Is in S, you need to show X minus E, the complement. The full set is now X. X minus E is in scripted as well. So that's what we want to do. Okay? So to show that, well, you got to show X minus E is in T. And that's obvious because X is in T. So remember there was a property earlier that we showed that the sigma algebra is also closed under set difference. Okay, sigma algebra is closed under set difference because set difference can be written as such. So set difference is X minus E is simply hold on a second, intersect with X minus intersect with the complement, right? So the complement here means y minus e. Y minus e. So that's x minus e. So you want the stuff in x that is not in e. So you intersect with the complement of e. And the complement is just y minus e. Because here, e is in t. E is in t. T is a sigma algebra over y. So y minus e is in t. Your work is great. Thank you very much. Well, I do the best I can. I can't. I'm not an expert in that. Okay, I'm just a guy trying to improve. And x is in t as well. So so overall, it just says that since x is in t and e is in t, e is in t follows from the definition of s. We have x minus e is in t. And always, and also x minus e is always a subset of x. This is always true. So therefore, x minus e satisfies the definition of s. X minus e is in t. X minus e is a subset of x. So therefore, x minus e is inscripted as needed. So second part done. All right, so let's continue. Cert. There we go. If we have, say, a sequence right now. So cert basically, cert needs to show closed under countable union. So for that, let E1, E2, and so on, the sequence of subsets be in S. Okay, be a sequence in S. All right, and now you have to prove the countable union closure property. So you need to show the union of n greater or equal to 1 is inscripted S. So that's what we want. Okay, so for that you need to show two things. The union, you got to show that the union is in T. And that's easy because by definition, since E1, E2 all the way are in scripted T, because every one of them is in T, and T is a sigma algebra, the union of all is in scripted T. Okay, so that's the first part, and you also need to show the union is contained in X. That should be easy because every single one of them is contained in X. So there you go. Since E1, E2 all the way are contained in X, so it's actually not hard at all. So it's just the union of them must also be contained in X. So satisfy the two definitions of S, therefore, conclusion, the union of En is contained in S. Is in S. It's not contained, but simply in S. So overall, therefore, this verifies that S is a sigma algebra. This is a sigma algebra. So in the light of this exercise, what can we say about the text? So go back to the text right here. In the main text, it commented that, hang on, let's do that real quick. And we'll comment on that real quick and I'll close the stream because it's been over 5 hours. All right, so here, what did it say? It says, we've been dealing with S measurable functions. We've been dealing with S measurable functions from an arbitrary set X to R in the context of an arbitrary set X R and sigma algebra big S on X. An important special case of this setup is when X is a Barreau subset of R and S is the set of Borel subset of R that are contained in X, which is exactly the setup here. So here in this exercise, big Y, actually here, big R, the reals, plays the role of Y. Plays the role of Y. And T, Borel sigma algebra plays the role of big T. And this big X is just the Borel subset, all right? And here, this scripted S contains the Borel sets that are contained by X, contained in X. The exercise 11 says there's a different way to think about this sigma algebra. So this sigma algebra can be also thought of as the result of intersection between X and a Borel set. Just take that. Just take an arbitrary Borel set, which may not necessarily be contained in X, and then take the intersection with X. And those two are the same. And it is indeed a sigma algebra. So this is something that we wanted to check. Right? Because here, it's simply by the description, it's not entirely clear that why this is a sigma algebra. So now this is verified, and we have an alternative description for that. So that's pretty cool. All right, so that's it for today. It's unfortunate we could only do 2 exercises. We'll continue this list next time, and the notes will be uploaded. Okay, thank you very much, everyone, for watching, and I'll see you next time. So just in case you guys didn't know, so actually today I did 2 streams together, which is like over 9 hours or something like that. That's kind of crazy, but I'm on vacation right now, so I have all the time in the world to do math. And tomorrow there's going to be actually a few activities, which, I mean, it's totally up to you if you want to participate. So tomorrow in the morning, actually not tomorrow, actually tomorrow in the afternoon. In the afternoon, I'll do a tensor analysis stream. And this is to prepare for the information geometry stream I'm planning to do in mid-August, early August actually. And at night I will do some information theory. Okay, if you guys are interested, stay tuned and have a good evening. Hey bro, is this stream for newbies or math for newbies in measure theory? Hi Explosion, welcome. How nice to have you on the stream. I remember you. You know a lot about number theory, I remember. This is for newbies in measure theory, not for newbies in math entirely, but I don't think you're a newbie in math. So all you need is some elementary analysis, okay? This is not what I said, this is Axler said. Go to the preface. Here. The prerequisite for using this book include a good understanding of elementary undergraduate real analysis. And for that, actually, Axel also prepared this supplement. The supplement here, this supplement should refresh your understanding of standard definition notation results from undergraduate real analysis. So go ahead, go to Axler's website and see if those things are familiar to you. Right, so here you have complete order field, which is basically the definition of R. The definition of R, you can use it axiomatically. You should just use the axiom of R, see if you're comfortable with the least upper bound and that sort of thing. Dedekind cut is optional. You don't need Dedekind cut for measure theory. Supremum, infimum, this is super important. And some of the consequences of completeness, including the density of real, that sort of stuff. Here you also have basic topology in Rn, closed and open and closed set. These are important. We've been using that quite a lot actually. And there you go. Some knowledge about the sequence of functions is also quite important, because later on actually we already seen that a sequence of measurable function is measurable. The limit of measurable function is measurable. You need to be comfortable with working with limit of sequences, not of just numbers, but also functions. So this is a very good collection of prerequisites, and see if you're comfortable with that. Sequence of continuity, that's what I just mentioned. Basically, those are the sort of things that are essential. And also the first chapter, the first chapter, Riemann integration, is also considered a review, and see if you're comfortable with those sort of stuff. Upper sum, lower sum, and all of those things. Anyway, I think that's enough for today. Thank you very much, everyone, for joining the stream.